Imagine looking up at the sky one day and watching it turn completely black. Not nighttime black, not storm cloud black, a black that swallows the sun for years. Now imagine that darkness is the reason you're one of only a few thousand humans left breathing on the entire planet. That's the story we're diving into today. 74,000 years ago, give or take, a volcano in what's now Indonesia didn't just erupt, it detonated. Scientists call it Toba, and some researchers believe it came close to erasing humanity before we ever really got started. The claim is staggering. Our entire species reduced to somewhere around 3,000 people. Not 3 million. Not 300,000. Just a few thousand survivors scattered across a world buried in ash and choked by cold. If that number is even close to true, then every single person alive today, all 8 billion of us, are descendants of a group so small you could fit them inside a high school auditorium. Think about that for a second. One eruption, one catastrophic afternoon in Earth's deep past, and humanity's entire future balanced on the genes of a tiny surviving population. But here's where it gets interesting, because scientists don't actually agree on this. Some say Toba nearly finished us off. Others say the evidence is shakier than it looks, that humans in some parts of the world barely noticed the eruption at all. So which is it? Did a single volcano almost end the human story, or is this one of those scientific legends that grew bigger with every retelling? That's exactly what we're going to dig into. We're going to walk through the geology of what made Toba so uniquely terrifying, the climate chaos it may have triggered, the ash layers still buried in soil on the other side of the world, and the genetic clues hiding inside your own DNA right now. We'll look at what the ice cores say, what the lake sediments say, and what actual human fossils and tools near the blast zone say. And we'll be honest about where scientists still argue, because this isn't a settled case. It's an active mystery. And that's what makes it worth exploring properly instead of just repeating the scary headline. Before we get into it, if you're listening to fall asleep, that's exactly why I make these. So tell me in the comments where you are and what time it is right now. I love checking in the morning and seeing London at midnight, Sydney at sunrise, Chicago somewhere in between. It's one of my favourite parts of doing this. Also, if you want the ad-free, music-free version of these videos, follow this podcast on Spotify. It's a much smoother listen, especially if you're using it to drift off. And if you've got a spare moment, a 5-star review genuinely helps this channel keep going. Links in the description if you want to leave one. Alright, let's get into it. To understand just how close humanity might have come to disappearing, we first need to understand what the world looked like before Toba ever erupted, because our ancestors were already living closer to the edge than you might think. Let's rewind the clock, not to 74,000 years ago just yet, but a bit further back to set the stage properly. Because before we can talk about a volcano nearly ending humanity, we need to talk about what humanity even looked like at that point. And the honest answer is, it wasn't much. Not in terms of numbers. Not in terms of security. Our species, biologically modern, anatomically pretty much like you and me, had been around for maybe 200,000 years by the time Toba blew. But around doesn't mean thriving. It doesn't mean spreading confidently across continents with cities and farms and stockpiled food. It means small, it means scattered. It means constantly one bad season away from disaster. Picture groups of maybe a few dozen people. Not hundreds. Not thousands. Small bands moving across landscapes that could shift from generous to brutal within a single generation. These weren't people settling down and building permanent homes. They were mobile by necessity, following herds, following rivers, following whatever patch of land happened to be producing food that particular year. If a water source dried up, you moved. If the animals migrated somewhere else, you followed. Staying still wasn't stability, it was a death sentence. Most researchers place these early populations of Homo sapiens primarily in Africa, though the exact regions are still debated. Eastern Africa shows up a lot in the fossil and genetic record. Southern Africa too, with sites suggesting sophisticated behaviour far earlier than once assumed. There's also growing evidence that different regions across the continent may have held their own semi-isolated populations, evolving somewhat independently before later mixing back together. Africa wasn't one uniform cradle of humanity. It was more like a patchwork of refuges, some connected, some not, depending on the climate at any given moment. And here's the part that really puts things into perspective. Homo sapiens weren't the only humans on the planet at this time. Not even close. Over in what's now Europe and Western Asia, Neanderthals were already established. Thick-boned, cold-adapted, skilled hunters who'd been dealing with Ice Age conditions for tens of thousands of years before modern humans even thought about leaving Africa. Further east, across Asia, a lesser-known group called the Denisovans were carving out their own existence, leaving behind so few fossils that for a long time we only knew they existed because of a single finger bone and some DNA sequencing that shocked the scientific world. There may have even been other human lineages we haven't fully identified yet. Ghost populations hinted at in genetic data, but never directly discovered in the fossil record. So when we talk about the world before Toba, we're not talking about a planet run by one confident human species. We're talking about multiple human populations, all relatively small, all vulnerable, all trying to survive in a world that kept changing the rules on them. It's a strange thing to picture, several different kinds of humans existing at the same time, none of them dominant, none of them guaranteed to be the ones who'd eventually take over the planet. Now, why was survival already so precarious before any supervolcano entered the picture? Because the climate itself was already unstable. This period, part of what's called the late Pleistocene, wasn't some gentle, steady backdrop. It was defined by dramatic swings, ice ages advancing and retreating, sea levels rising and falling by dozens of meters, entire ecosystems shifting locations over the course of a few thousand years. Some of these swings happened slowly enough for populations to adapt. Others happened fast, geologically speaking, fast enough to devastate groups that couldn't move quickly enough or find a new food source in time. Droughts could last generations. Cooling periods could turn grasslands into deserts. A river that had supported a group for decades could simply stop flowing. And when that happened, there was no fallback system, no stored grain, no global trade network, no way to call for help. You adapted, you migrated, or you died out. That was the reality. This is really the key idea to hold on to before we get into Toba itself. Humanity was never on some guaranteed path to dominance. Extinction was always a live possibility. Small populations, spread thin, dependent on unpredictable environments, are exactly the kind of populations that can vanish without leaving much trace at all. When we look back now, it's easy to assume our species was destined to succeed. But nothing about the fossil or genetic record supports that kind of confidence. We were fragile, we were few, and we were constantly gambling against forces completely outside our control. Which brings us to a term you're going to hear a lot throughout this video: bottleneck. In plain language, a population bottleneck is what happens when a species' numbers drop so low and stay low long enough that it leaves a permanent mark on the genetics of everyone who comes after. Think of it like squeezing a crowd of people through a narrow doorway. Only some make it through, and everyone on the other side, everyone descended from that surviving group, carries a kind of genetic echo of that squeeze. Less variety, shared traits. A smaller, more uniform starting point for the population that eventually grows back. Bottlenecks matter enormously for questions of ancestry because they can be detected sometimes long after the fact, hidden inside our DNA, like a scar that never quite fades. And this is exactly why Toba became such a tempting suspect, because something at some point appears to have squeezed our species through a very narrow doorway indeed. So what could squeeze an entire species like that? To even be a suspect, you need something far beyond a normal volcanic eruption. You need a monster. Meet Toba. If you look at a modern map of Sumatra in Indonesia, you won't see a smoking cone or a classic volcano silhouette. You'll see a lake, a huge one. Lake Toba is about 100 kilometers long, shaped like a rough oval gouged into the spine of the island. Inside that lake is an island, Samosir, rising up where the magma once pushed the crust back toward the sky. The whole thing isn't just near a volcano, it is the volcano. You're staring at the scar. Toba sits along the Sunda Arc, where the Indian-Australian tectonic plate is diving under the Eurasian plate. That subduction zone is one of Earth's great factory lines for volcanoes. As the oceanic plate sinks, it heats up, water is driven off, rock melts, and magma starts rising. Most of the time, that gives you a chain of ordinary stratovolcanoes. Dangerous, sure, but familiar. Cones, craters, occasional eruptions that local people learn to live with. But sometimes, if the conditions are just right or just wrong, that rising magma doesn't leak out in a series of frequent small eruptions. It pools, it accumulates in enormous underground chambers, rich in dissolved gases under pressure for tens of thousands of years. That's the setup for what geologists call a supereruption. Supereruption isn't a dramatic YouTube word, it has a technical meaning. Volcanologists use something called the Volcanic Explosivity Index, the VI, to compare eruptions. It's a logarithmic scale, like the Richter scale for earthquakes. Each step up means roughly 10 times more material blasted out. The eruption of Mount St. Helens in 1980, VI5. The 1883 Krakatoa eruption, VI6. The 1815 eruption of Tambora, also in Indonesia, which triggered the famous year without a summer in Europe and North America, VI7. A supereruption is VI8. That's the top of the scale. To qualify, an eruption has to eject at least 1,000 cubic kilometers of magma in the form of ash and pumice. Not 1,000 cubic meters, 1,000 cubic kilometers. Imagine a cube 10 kilometers tall, 10 wide, 10 long, carved entirely out of molten rock. Then, multiply that by another 10. That's the sort of volume we're dealing with. Toba seems to have cleared that bar. Many estimates put its erupted volume in the range of 2,800 cubic kilometers of material. Not all of that blasted vertically in one single jet, but the total output of the system during the main event is in that neighborhood. That's why when scientists talk about supervolcanoes, Toba is always in the front row. But a supereruption isn't just about sheer volume. It's also about how the eruption unfolds. At some point around 74,000 years ago, pressure in Toba's magma chamber built past what the overlying crust could handle. The roof failed. When that happens in a system this big, you don't just get a lava fountain. You get what's called a runaway eruption. First, an eruption column punches into the sky, a pillar of ash, pumice, gas, and shattered rock roaring upward at hundreds of meters per second. For Toba, modelling suggests this column could have reached the lower stratosphere, possibly 30, 40, maybe even over 50 kilometers high. Once material gets that far up, it's not just falling back down on the local forest. It's entering the global circulation. Closer to the vent, the column becomes unstable. Parts of it collapse under their own weight, generating pyroclastic flows, dense, ground-hugging clouds of hot ash, pumice and gas that can race across the landscape at highway speeds or more, at temperatures that incinerate anything living in their path. Around Toba, these flows would have been truly gargantuan, filling valleys, overtopping ridges, burying entire drainage systems in meters to tens of meters of welded ash. Farther away, lighter ash particles fell like a global snowfall. In some regions, they might have accumulated in layers thick enough to choke rivers and smother vegetation. In others, they would have been a dusting, still enough to contaminate water sources and make breathing difficult. Some ash would have settled out quickly, some would have stayed aloft, riding winds, circling the planet. And while the main explosive phase might have been the headline event, supereruptions often come with a long tail. The system doesn't just switch off. There can be weeks, months, even years of diminished, but still dangerous activity, minor eruptions, gas emissions, lingering thermal anomalies, resurgent domes forming in the collapsed caldera. Toba likely didn't go from quiet to apocalyptic to silent in a single afternoon. It was more like a massive heart attack with aftershocks. So, how does this stack up to eruptions we've actually seen? Tambora in 1815 was big enough to cool global temperatures by something like 0.5 degree to 1 degree Celsius for a year or so, disrupt monsoons, trigger crop failures, and help plunge parts of the northern hemisphere into famine. Yet in terms of volume, Toba was probably an order of magnitude larger. Krakatoa shattered an island, generated tsunamis, and produced sunsets so spectacular that painters and poets wrote about them for years. But its output is dwarfed by Toba's. Even the most infamous historical eruptions, the ones that show up in textbooks and climate reconstructions, are likely just local rehearsals compared to what Toba did. That's why it enters any conversation about global-scale impacts and potential bottlenecks. It's one of the very few eruptions in the last couple of million years that seems physically capable of perturbing the entire Earth system at once. Of course, we didn't have any human eyewitnesses taking notes. No diaries, no court chronicles, no ship logs full of ash reports. So how do scientists reconstruct any of this? They read the debris. Around Lake Toba itself, there are deposits of ignimbrite, welded pyroclastic flow material, tens to hundreds of meters thick. The extent of these deposits tells you how far those flows travelled and how voluminous they were. The texture and chemistry of the ash grains reveal how gas-rich and explosive the magma was. Distinctive shards of Toba glass, with a recognizable chemical fingerprint, show up in sediment cores taken thousands of kilometers away, in the Indian Ocean, in the Arabian Sea, even as far as East Africa. By tracking where those microscopic grains are found, and how thick the layers are, researchers can map the spread of the ash cloud. They can also model the height of the eruption column from the distance ash travelled and the size of the particles that made it that far. They can estimate eruption duration from the layering within deposits, sharp contacts suggesting sudden pulses, gradations hinting at waxing and waning intensity. They can use radiometric dating to pin down when the different phases of activity happened. All of this is indirect, of course. It's interpretation layered on evidence, not a replay of security camera footage. But when multiple lines of data, field mapping, geochemistry, computer models converge, a picture emerges. Not a perfect one, but detailed enough to say this was no ordinary eruption. This was a planetary scale event, and that's the crucial point for the rest of our story. Toba wasn't just a local disaster for Sumatra. It was big enough, fast enough, and high-reaching enough to plausibly affect climate, ecosystems, and human populations far beyond the immediate blast zone. Before we get into exactly how scientists try to reconstruct those global consequences and what they think Toba did to the climate, a quick note. If you're the kind of person who likes to go straight to the source, we've put together a list of accessible books and papers on supereruptions and human evolution. You can find them, plus a viewer discount on a couple of titles, at the link in the description and on our site. Check that out if you want to dig deeper into the primary research behind all of this. Because next, we're going to push further into the evidence. How do we know when Toba erupted, how long it lasted, and just how big the blast really was? To answer those questions, we have to zoom in on something that sounds incredibly dull on paper, but turns out to be one of the coolest detective tools in geology: ash chemistry. When a volcano erupts, it doesn't just throw out generic ash. Those microscopic glass shards carry a chemical signature, specific ratios of elements like silicon, aluminum, iron, magnesium, trace elements like zirconium or rare earths. The exact mix depends on the magma's history, what rocks it melted, how long it sat underground, how much gas it held. That means every big eruption leaves behind something like a fingerprint. Scientists take tiny samples of glass shards from different layers of sediment, melt them with an electron beam, and read off their chemistry. If the composition matches what we know from Toba's deposits in Sumatra, same silica content, same trace elements, same ratios, that layer, wherever it's found, probably came from Toba. That's how we can link a thin smear of ash in a lake in East Africa, a layer in the Arabian Sea, and a dusting in Indian Ocean sediments all back to the same supereruption. Even when the ash is so fine you need a microscope to see it, the chemistry tells you this is Toba. This tephra fingerprinting is what turns scattered local clues into part of one global crime scene. Without it, a layer of ash in India would just be some volcano sometime. With it we can say, with reasonable confidence, this is the fallout from the same event that carved Lake Toba's caldera. But knowing who isn't enough. We also want to know when. That's where dating tools come in, and where things get messy. One workhorse method is radiometric dating, especially argon-argon dating on volcanic minerals. When magma cools, certain minerals lock in isotopes of potassium and argon like tiny atomic clocks. Over time, radioactive potassium decays into argon at a known rate. Measure the ratio and you get an age. For Toba, multiple argon-argon dates cluster around roughly 74,000 years ago, give or take a few thousand years. Some studies have nudged it a bit older or younger, depending on calibration, sample quality, and which standard they used. We're not talking about knowing the exact day, or even the exact century. We're talking about a window of a few thousand years that almost certainly includes the main eruption. Then there's stratigraphy, the simple but powerful fact that in undisturbed sediments, younger layers sit on top of older ones, in lake cores, ocean mud, and exposed outcrops. The Toba ash layer turns up sandwiched between other sediments we can date using different methods, like oxygen isotope cycles tied to glacial interglacial patterns, or radiocarbon for younger material above it. By cross-checking radiometric dates with where the ash sits in these stacked layers, researchers can narrow down the timing. If the ash lies between two well-dated climate events, for example, it must have fallen sometime in between. Of course, all of this comes with uncertainties. Radiometric dating has error bars. Sediments can be disturbed. Different cores might stretch or compress time differently because of changes in how fast material was being deposited. So when you hear Toba erupted 74,000 years ago, understand that as shorthand for sometime around 74,000 years ago, plus or minus a bit, not a precise timestamp. Once you've got the fingerprint and a rough date, the next question is, how big was this thing really? One way to get at that is surprisingly straightforward. Map how thick the ash is and how far from the source it goes. Around Toba, pyroclastic flow deposits can be hundreds of meters thick. In India, the famous Toba ash can be several meters thick in places. Farther away, it thins to just a few centimeters, then millimeters, then microscopic traces in deep sea mud. If you map those thicknesses across thousands of kilometers and model how an ash cloud would spread given prevailing winds and eruption column heights, you can back-calculate a rough erupted volume. That's how volcanologists arrive at those huge numbers, thousands of cubic kilometers of material. But ash on land is only part of the story. Most of the planet is ocean, and the oceans are quietly storing a lot of Toba's debris. Ocean sediment cores, long cylinders of mud pulled up from the seafloor, are like slow-motion tape recorders. Year after year, particles settle out of the water and accumulate. When Toba blew, its ash rained down into the Indian Ocean, the Arabian Sea, the Bay of Bengal. Today, thin but distinct layers of Toba glass show up in those cores, linked back to Sumatra by that chemical fingerprint. Ice cores from places like Antarctica and Greenland add another dimension. They don't usually capture visible Toba ash, those particles mostly dropped out before reaching the poles, but they do record volcanic signals, spikes in sulfate, tiny changes in acidity, sometimes trace elements. There's ongoing work trying to match those volcanic signals to Toba's timing, though it's not as clean as seeing a big black stripe of ash. Taken together, these global archives, lake mud, ocean cores, ice, don't just tell us Toba happened. They show how far its effects travelled, how abruptly that ash arrived, and in some cases how the environment responded in the years right after. So why, if we have all these tools, do size estimates still vary? Partly because reconstructing an eruption from fragments is like trying to rebuild a shattered vase when half the pieces are still buried. Erosion removes ash. Later eruptions can bury or mix deposits. Some regions were never sampled, or the cores we have are too coarse to capture very thin layers. On top of that, the models we use to turn thickness over distance into total erupted volume have assumptions baked in about wind speeds, eruption duration, how much ash was blown high versus slumped into pyroclastic flows. Tweak those assumptions and your volume estimate shifts. That's why you'll see a range in the literature. Some studies put Toba's main eruptive volume closer to 2,000 cubic kilometers. Others push it up toward or beyond 3,000. There's debate over how much material belongs to the single catastrophic phase versus pre- and post-eruptive activity. What most researchers agree on, though, is the order of magnitude. Whatever the exact number, Toba comfortably sits in VI8 territory. It's one of the largest known eruptions in the last couple of million years, and certainly one of the best documented supereruptions of that scale. And that's enough for our purposes. We don't need to know whether it was 2,500 or 2,900 cubic kilometers to ask the big questions. What does a blast like that do to climate? To ecosystems, to scattered, vulnerable human populations already living close to the edge? To explore that, we have to follow the ash itself into the atmosphere, across continents, and down into the oceans. In the next section, we'll track what happened after Toba blew, the fallout, the darkness, and the immediate hazards that would have reshaped entire regions in the weeks and months after the sky turned to stone. When we talk about ash, it's easy to imagine something like campfire soot, light, fluffy, annoying, but harmless. Volcanic ash is not that. Volcanic ash is powdered rock and glass. The particles can be as sharp as ground-up razor blades. In a supereruption like Toba, those particles are blasted tens of kilometers into the sky, then carried by winds and gravity over areas the size of continents. Close to the volcano, the ash doesn't fall, it crashes. In the near field, ash can accumulate in meters. That kind of load collapses roofs, caves in shelters, and turns forests into mangled heaps of broken branches. If you're breathing that air, every inhale drags microscopic shards into your nose, throat, and lungs. Some gets coughed out, some sticks, some stays there for life. For humans and animals, that means burning eyes, inflamed airways, and a massive spike in respiratory problems. If you already have any weakness, child, elder, injured, this is the kind of environment that can kill you slowly over days or weeks, even if you survived the blast itself. Water doesn't escape either. Heavy ashfall chokes streams, clogs springs, and turns clean water into a grey, abrasive slurry. In a few hours, a clear river can become a moving layer of mud. Ash settles in pools and seeps, coating everything in a film of fine grains that scratch teeth and wear down grinding surfaces on tools and food. If your survival strategy depends on knowing which water hole is safe, Toba just scrambled that map. Then there's mobility. Walking through thick ash isn't like walking on sand. It's more like trudging through flour that sucks at your feet and hides every rock and hole underneath. For humans, that means blisters, sprains, broken ankles. For hoofed animals, it means cracked hooves, infected cuts, and sometimes being literally stuck in place when ash mixes with rain and turns to cement-like sludge. Shelter, the thing you most want in this situation, becomes a double-edged sword. Caves might protect you from the initial fallout, but if ash keeps piling up at the entrance, you risk being sealed in or suffocated by air thick with dust. Simple brush shelters and thatched roofs, they collapse under the weight, sometimes in the middle of the night, turning safe spaces into death traps. So what does this mean at the scale of continents, not just valleys? Here's where we have to be precise about scale. Around Toba and downwind across parts of what's now Indonesia, Malaysia, maybe into parts of India, we're talking about true regional devastation. Landscape transforming levels of ash, whole ecosystems reset. For people in those zones, survival might mean weeks or months of chaos, followed by years of trying to live in a world where almost every familiar resource has changed or vanished. Farther away, though, the story softens. Instead of meters of ash, you might get centimeters, or even just a thin dusting. In those regions, ash is less a crushing weight and more an abrasive nuisance. It fouls water, irritates lungs, damages plants, and makes travel miserable, but it doesn't necessarily erase the landscape. Think of it as a gradient, from world ending near the source to world complicating thousands of kilometers away. That gradient matters enormously for humans who are already scattered and living on narrow ecological margins. Start with plants. A thick ash blanket can snap branches, strip leaves, and bury seeds. Many plants simply suffocate under the weight or lose the ability to photosynthesize. But some grasses and shrubs can punch through thin ash layers. Some seeds actually germinate better in disturbed soils. Over time, years to decades, vegetation starts to return. But over time doesn't help if you need to eat this month. Herbivores, grazers and browsers are hammered first. Their food is either buried or toxic. When they do find plants, those leaves and stems are coated in ash that wears down teeth like sandpaper. Animals lose weight, get infections, and, in the worst hit areas, crash in numbers. Predators then feel the shock a little later. Fewer herbivores means less prey. Hunters have to roam farther, risk more, and compete harder. Exactly the pressure you don't want when you're a small band of humans depending on the same animals for meat, skins, and bones. For human foragers, the familiar food web becomes both unpredictable and fragile. Some wild tubers might still be accessible under the ash. Some shellfish along coasts might be relatively unaffected. In a few pockets, ash might even preserve moisture in the soil and create short-term oases of plant growth. But overall, the effect is to scramble the pattern of where food is and how long it lasts. And that's before we talk about visibility. Imagine waking up to a world where the sun is a pale disk behind a permanent haze, and the horizon has literally disappeared. Thick ash in the air can cut visibility to a few meters. Even thinner ash layers on the ground erase paths, watercourses, and landforms you've used as markers for generations. Rivers become just faint, grey depressions. Forests become skeletal silhouettes. If your navigation is based on reading landforms, recognizing distant hills, or following animal tracks, that entire mental map stops working. Journeys that used to take a day might take 3 if you're willing to risk them at all. Social contact changes with the landscape. Neighbouring groups you used to meet seasonally might now be physically cut off by belts of heavy ash or zones of dead forest. Even where travel is technically possible, the cost goes up. More energy, more water carried, more risk of injury. Bands that once exchanged mates, tools, and information could find themselves isolated at exactly the moment when they most need allies. So how do you survive in an ash-blanketed world? You adapt fast. One obvious strategy is to hug the edges. Stay near water sources that are still flowing and not completely choked with ash. That might mean moving toward coasts, bigger rivers or lakes where dilution keeps water usable. Another is vertical movement. Higher ground might escape the worst of the ash in some wind patterns, while sheltered valleys might trap it. Groups that could read where ash was thickest versus thinnest would have an advantage. Shelter has to evolve. Instead of flimsy surface structures, you might favour rock overhangs, deeper caves with better ventilation, or shelters partly dug into slopes where ash can slide over the top. Coverings over entrances, more sophisticated fire use to drive ash-laden air upward, and frequent relocation to avoid structural collapse all become critical. Breathing becomes a technological problem. Even simple solutions, using damp animal skins, plant fibres, or woven mats over the mouth and nose, could dramatically reduce inhaled ash. People who noticed that staying low, avoiding outdoor activity during peak fallout, and keeping living spaces as dust-free as possible improved survival would be more likely to pass those habits on. Diet shifts too. Instead of relying heavily on large grazers that have been decimated, groups might pivot harder toward underground storage organs, nuts, insects, fish, and shoreline resources. Ash can smother inland ecosystems, but it has a harder time killing everything in a tidal zone. Knowing how to exploit those refuges becomes a life or death skill. And there's a social strategy: stay connected where you can. Even if long-range journeys become rare, short-range scouting and information sharing about where ash is thin, where animals are still migrating, where water is clear, those become some of the most valuable pieces of knowledge on Earth. By the way, if you're the kind of person who wants to dig deeper into this kind of past catastrophe, we've partnered with several publishers to offer discounts on science and history books through our site. You can check current deals at humanthresholds.com whenever you're ready to go beyond the video. All of this, ash in lungs, poisoned water, invisible horizons, is the immediate, brutal face of a supereruption. But the ash cloud doesn't just fall. It also hangs in the sky, feeds chemical reactions, and sets the stage for something bigger and longer lasting: changes in the entire planet's climate. To understand how Toba might have dimmed the world not just for days or months, but for years, we have to leave the ground and follow the finest particles and gases into the stratosphere. That's where the story of volcanic winter begins. When a volcano like Toba blows, it doesn't just throw rocks and ash into the sky. It also injects a huge amount of gas. One gas matters more than almost anything else for climate: sulfur dioxide. Down near the surface, sulfur dioxide is nasty but short-lived. It reacts with water, gets rained out, and you're done. But Toba didn't just puff sulfur into the lower atmosphere. It punched it into the stratosphere, more than 20 kilometers up, above most of the weather. Up there, the chemistry changes. Sulfur dioxide reacts with water vapor to form tiny droplets of sulfuric acid. Not big raindrops, but microscopic spheres, each one a perfect little mirror. These are sulfate aerosols, and once they're in the stratosphere, they can hang around for years. Those aerosols don't care about your local weather. They sit above the clouds, forming a thin, hazy veil around the planet. When sunlight hits that veil, part of it gets reflected back into space before it ever reaches the ground. Less sunlight at the surface means less energy. Less energy means cooling. This is the basic physics behind volcanic winter. A planet with a slightly better sunshade. Now, this doesn't turn Earth into a snowball overnight. The timescales matter. The ash we talked about before settles out in days to weeks, especially the heavier particles. You can get dramatic local darkness, choking fallout, maybe a few very dim weeks over a wide region. But ash is gravity's problem. It falls. Sulfate aerosols are different. They're so small that they drift. Winds in the stratosphere spread them around the globe. After a big eruption like Pinatubo in 1991, it took a few months for the aerosol cloud to wrap around the planet, and then global temperatures dipped for about 2 to 3 years. Toba was orders of magnitude larger than Pinatubo in erupted material. That doesn't automatically mean orders of magnitude more cooling, but it does mean we're likely talking about a much thicker and more persistent aerosol veil. So what's plausible? Most researchers who model Toba's climate impact land somewhere in the range of a few degrees of global average cooling for a handful of years, maybe up to a decade or so of noticeably altered climate. Some simulations push it harder, with longer lasting or deeper cooling. Others are more conservative, especially when they factor in uncertainties about exactly how much sulfur Toba released and how efficiently it reached the stratosphere. But here's the key. A few degrees sounds mild until you realize how uneven that cooling can be. The planet doesn't cool like a refrigerator. It cools like a nervous system, with some parts going numb, while others twinge and spasm. Take the tropics and monsoons. Monsoon systems are driven by temperature contrasts between land and ocean. Heat up land faster than sea in summer. Air rises over land, moist air rushes in from the ocean, and you get seasonal rains that millions of people, and back then millions of animals and plants depended on. Change the sunlight, and you change those contrasts. Some models of large eruptions show weakened monsoons, shorter rainy seasons, later onset, patchier coverage. For groups living on seasonal rainfall, relying on plant growth that tracks a predictable wet season, this isn't just a bit drier, it's the grasses came late, the herds moved differently, the wild fruits didn't ripen when they were supposed to. Farther from the equator, the jet streams and storm tracks shift, cool the planet unevenly, and you can move the paths of major storms north or south. Regions that used to get regular winter snow might suddenly find themselves on the dry side of the storm belt. Others might be hammered by more frequent or more intense storms. From the point of view of small human groups, this doesn't show up as a smooth global temperature line. It shows up as a string of bad years, and that's why global averages can be so misleading. Imagine a graph that says average temperature down by 2 degrees Celsius for 5 years. That sounds survivable. Put on a coat, build a better shelter. But averages hide the extremes. That same shift might mean that in some regions, summer temperatures hardly change at all, while winter nights drop an extra 5 or 10 degrees below what local life is used to. A slightly cooler world on paper can translate, in reality, into 1 or 2 catastrophic winters in a row. Winters where marginal plants die back, where animals that normally scrape through starve instead, where rivers freeze a little longer and deeper. For foragers living without surplus storage, those few bad seasons can be the difference between slow growth and demographic collapse. To figure out which of these scenarios is more realistic for Toba, scientists turn to models. Climate models are essentially giant sets of equations that try to capture how air, water, radiation, and chemistry interact. To simulate a volcanic winter, researchers feed in estimates of how much sulfur reached the stratosphere, how high it went, and where, then let the virtual atmosphere evolve. Some models are relatively simple. They average conditions across wide bands of latitude and focus on whole planet responses. Others are high-resolution monsters that track regional patterns of rainfall, storm tracks, and seasonal temperature swings. This is where the disagreements start. Change the assumed sulfur output, and you change the thickness of the aerosol veil. Change the particle size, and you change how long it stays aloft. Assume different wind patterns in the stratosphere, and the cloud spreads differently between hemispheres. Layer uncertainties in the background climate, ice sheets, sea surface temperatures, greenhouse gas levels, and you get a family of possible outcomes, not a single answer. Some simulations produce a severe, prolonged cooling that could, in principle, stress ecosystems worldwide. Others show a sharp but relatively brief perturbation, a few bad years, then a slow return toward baseline. Many agree on one thing, though. The tropics don't necessarily become uninhabitable ice fields. They become more unpredictable, and that's the crucial point for our story. Toba doesn't have to freeze the entire Earth solid to matter. It just has to nudge rainfall patterns, shorten growing seasons, and add a layer of climatic chaos on top of an already unstable Ice Age world. For scattered bands of humans recovering from earlier crises, that combination of haze, cooler temperatures, and messed-up seasons might be far more dangerous than any single drop in the global average. The question is, did it push our species to the brink numerically, the way some have claimed, or did humans ride out the volcanic winter with more resilience than the most dramatic models suggest? To answer that, we need evidence that isn't just simulated. We need to see what actually happened in ice, in mud, and in the layered records of Earth itself. If you want to know what really happened after Toba, you have to go to the places that don't forget. Start with ice. Deep inside the Greenland and Antarctic ice sheets, snow has been piling up for hundreds of thousands of years. Each year's snowfall gets buried, compressed, and turned into a new layer of ice. Drill straight down, and you're basically time-traveling through winters. Inside that ice, tiny bubbles of ancient air are trapped. Dust, ash, and chemicals get locked in too. Among those chemicals is sulfur. When a big volcano blows, some of that sulfur eventually falls out of the sky and lands on polar snow. Years later, you can see it in an ice core as a spike in sulfate concentration. Stack those spikes up, line them with depth, and you get a timeline of volcanic activity. At least that's the ideal. In reality, ice cores are powerful, but they're not magic. They can tell us there was a large injection of sulfate into the atmosphere. They can hint at how big it was, and sometimes whether it was more likely tropical or polar based on which cores see it most strongly. In the very recent part of the record, where the layers are thick and clear, you can often say, this spike corresponds to this eruption in this year. But 74,000 years ago is not the recent part of the record. By the time you're that deep, individual annual layers have been thinned out by the slow flow of ice. They stretch, smear, and compress. Dating becomes fuzzier. Instead of this year, you get this few decades, or this century-ish. Different cores give slightly different chronologies. Researchers have to cross-match them using patterns of known events, like magnetic shifts or large, clearly dated eruptions closer to the surface. So when we look for Toba in the ice, we don't get a glowing neon sign that says, "Here it is." We get a set of sulfate spikes, some large, some modest, with age estimates that come with error bars of hundreds of years. And then there's the other problem. The atmosphere is never quiet. Even without Toba, the ice record around that time shows multiple volcanic spikes. The Pleistocene was a busy era for volcanoes. Some of those spikes could be Toba or its precursors. Others could be completely unrelated eruptions, half a world away. Sulfate in an ice core doesn't carry a label saying which volcano it came from. To tighten the story, scientists look beyond the poles into the mud at the bottom of the oceans. Marine sediments are layered time capsules too. Year after year, tiny particles of dust, dead plankton, and chemical precipitates rain down to the seafloor. Over tens of thousands of years, they pile up in thin, almost paper-like layers. Drill into those, and you get an archive of ocean conditions. Inside those layers are microfossils, microscopic shells of organisms like foraminifera. The chemistry of those shells is sensitive to temperature. Ratios of oxygen isotopes, for example, shift depending on how warm or cold the water was when the organism built its shell. Measure those ratios through the core, and you get a squiggly line of past temperatures. You can also see changes in dust, how much wind-blown material was reaching the ocean, from where and in what size. A sudden increase in certain types of dust might suggest drier conditions on nearby continents. Stronger winds or both, exactly the kinds of changes you'd expect if a volcanic winter altered rainfall patterns. So scientists search around the depth that should correspond to 74,000 years ago and ask, do we see a recognizable cooling fingerprint? A shift in dust? A disturbance in ocean productivity? They do see changes around that time, but again the story isn't simple. The Earth was already in a glacial phase. Ice sheets were growing and retreating in complex rhythms paced by orbital cycles. Over thousands of years the climate was swinging on its own, long before Toba threw in an extra disturbance. When you're reading an ocean core, a volcanic blip might be riding on top of a much larger, slower climate trend. That's like trying to pick out a single drumbeat in the middle of an orchestra. On land we get another angle, lakes. Many lakes, especially deep, quiet ones, build up sediments just like the ocean. Fine layers of silt, organic matter, and sometimes annual bands called varves can record seasonal changes. When volcanic ash falls on a lake, it leaves a distinctive layer, often a thin, bright band of glassy particles that stands out from the mud above and below. That ash layer is a timestamp. If you can chemically match that ash to Toba's composition, you've found the moment Toba's fallout reached that lake. Now you can look at what happens in the mud directly above it and directly below it. Do pollen grains from warm-adapted plants suddenly disappear after the ash and get replaced by cold-loving species? Do the microfossils change in a way that suggests the water became colder, or more stratified, or more nutrient-rich? Does organic content drop, hinting that productivity crashed for a while? In some regions, especially downwind of Toba in South Asia, cores that contain its ash do show environmental shifts, changes in vegetation, hints of drying, perhaps cooler conditions. In others, the signal is more muted. Life goes on with adjustments, but not total collapse. The trick is separating what Toba did from what the climate was already doing. At 74,000 years ago, there were other climate events in play. Stadials and interstadials, shorter-term cold snaps and warm pushes woven into the larger glacial cycle. Some cores show changes that might line up with known global events, like Greenland temperature swings. Others are more local, driven by regional rainfall patterns and geography. So researchers cross-compare ice, ocean, and lakes. Does the sulfate spike in ice roughly align with a cooling pulse in the ocean record? Does that cooling pulse line up with vegetation changes in lake sediments that sit right above a Toba ash layer? If multiple independent archives, dated with different methods, all point to a disturbance in the same broad window. Confidence goes up that we're seeing Toba's hand on the climate. But broad window is the operative phrase. By the time you're 74,000 years back, you're not getting neat year-by-year diaries. You're getting blurry snapshots. Ice cores might resolve down to decades at best. Ocean sediments might average conditions over centuries. Lake cores can sometimes be higher resolution, sometimes not, depending on how fast they accumulate. Add dating uncertainties, radiometric ages with plus-minus ranges, layer counts that can skip or double, and the idea of assigning exact calendar years to specific Toba impacts becomes more hope than reality. This is why claims like Toba caused X years of Y degrees cooling starting in exactly year Z are almost always simplifications. The real evidence is messier and more probabilistic. Overlapping signals, approximate dates, patterns that suggest rather than decree. If you're curious how scientists wrangle all of this into a coherent picture, we have a deeper reading list and sources collected at our site, mindsaftermidnight.com, with a discount link for viewers on a few excellent books about paleoclimate and human evolution. Check that out if you want to see the raw graphs and core data behind the story. For now, keep this in mind. Earth's memory is long, but it's not perfectly sharp. The ice, the oceans, and the lakes all agree that Toba happened and that it mattered. They also agree on something else. Toba erupted into a world that was already unstable. To understand whether it really pushed humans down to just a few thousand survivors, we have to combine these environmental records with another kind of archive, not in mud or ice, but in our own cells. When people say humanity was reduced to 3,000 individuals, it sounds like a census. It isn't. That number comes from something called effective population size, and that's a very different beast from how many people were actually alive. Effective population size is a genetic concept. Imagine you're trying to figure out how big a population was in the past, not by counting bodies, but by looking at how much genetic variation survived into the present. You work backwards from today's DNA and ask how many breeding individuals, over how much time, would produce this pattern of diversity and relatedness. It's like walking into a crowded room and judging how many families are represented, not by counting heads, but by looking at how similar everyone's faces are. A population of 10,000 people where only a few hundred are having kids each generation can behave, genetically, like a population of just a few hundred. On the flip side, a population that's structured into small groups, with some inbreeding and some isolation, can look genetically smaller than the true head count. So, when you hear 3,000 humans left on Earth, what the genetic studies are usually saying is closer to, for a long stretch of time, our ancestors' gene pool behaved as if it were being drawn from roughly 3,000 breeding individuals. Not that there were exactly 3,000 terrified people huddled around a single fire waiting for the ash to settle. Still, how did we get that specific, dramatic number? The earliest hints came from mitochondrial DNA in the 1980s and 90s. Mitochondria are those energy-making structures in your cells, and they have their own tiny genome passed down almost entirely from your mother. That makes mtDNA a handy time capsule. It accumulates mutations at a roughly predictable rate, and because it doesn't recombine like the rest of your DNA, its genealogy is easier to reconstruct. Researchers sequenced mtDNA from people around the world and found something striking for a species scattered across the globe. Humans didn't have that much mitochondrial diversity. By plugging that low diversity into population genetics models, and assuming certain mutation rates and generation times, they inferred that our mitochondrial effective population size had been small for a long time in the Pleistocene, on the order of a few thousand breeding females. Convert that to total breeding individuals, add in males, and you land in the familiar about 10,000 for long-term humans, with specific bottlenecks sometimes framed as maybe just a few thousand. Later, more sophisticated studies using nuclear DNA, the 3 billion base pairs in your chromosomes, refined the picture. They too saw signs of reduced diversity and past contractions. Some models, under particular assumptions, generated headline-friendly numbers, dips down to 1 or a few thousand effective individuals at certain times in our history. From there, the story often took on a life of its own. Effective size of a few thousand became only a few thousand humans left. A few thousand became 3,000. 3,000 over a long period, merged in popular imagination with 3,000 huddled together after Toba. It's compelling. Our brains like sharp turning points and close calls. Almost everyone died. Only 3,000 survived. Feels like a movie plot. For a long time, our ancestors lived in relatively small structured populations that limited genetic diversity sounds vague and unsatisfying. But if we're being careful, we have to admit that the genetics alone don't tell us that Toba was the gun that almost killed us. They don't even demand a sudden global catastrophe. There are at least two big categories of explanation for low genetic diversity. One is the dramatic one, a sudden, short-lived bottleneck. Something awful happens, an eruption, a pandemic, a rapid climate shift, and population size plunges over a few centuries or millennia before recovering. In the DNA, that can look like a sharp constriction in the ancestral branches, a narrowing of the family tree at a certain time. The other is quieter, long-term small population size. If our ancestors spent hundreds of thousands of years in scattered groups, never very numerous overall, with patches of local extinction and recolonization, the end result can be similar. You still get a shallow tree and low diversity, but you didn't need a single apocalyptic day to make it happen. Just constant pressure, limited habitat, and the slow grind of Pleistocene climate swings. And their structure, if you have many small groups partially isolated from each other, exchanging mates now and then, they can drift genetically in ways that mimic bottlenecks when viewed from the far future. To models that assume a single, well-mixed population, structured meta-populations can look like size changes even if the total number of humans never actually crashed that low at once. This is why scientists are cautious about tying that 3,000 directly to Toba. To seriously claim that the supereruption nearly wiped us out, you'd want multiple lines of evidence to line up. On the genetic side, you'd look for a bottleneck signal specifically dated around 74,000 years ago, using methods that can resolve that timescale. You'd want it to show up consistently across different parts of the genome, in different global populations, and under different modelling assumptions. On the environmental side, you'd want clear signs of a severe, global, decades to centuries-long climatic shock, which we've started to explore in the ice, ocean, and lake records. On the archaeological side, you'd hope to see abrupt breaks, sites abandoned, tool traditions disappearing, human fossils becoming vanishingly rare in the layers that immediately follow Toba's ash. If instead the genetic bottleneck looks smeared over hundreds of thousands of years, if the climate archives show disturbances, but not a unique planet-wide catastrophe, and if the archaeology near and far from Toba shows continuity rather than disappearance, then the 3,000 survivors story starts to look less like a near-instant global die-off and more like a long, hard squeeze on a species that was already living close to the edge. In the rest of this video, that's the standard we're going to use. Whenever we talk about near extinction, we'll ask, do the genetics, the climate records, and the archaeology all point in the same direction at the same time, with enough precision to blame Toba? To answer that, we need to take a closer look at what those genetic tools actually do, what mtDNA, Y-chromosomes, and whole genome studies can and can't tell us about ancient population crashes. So let's zoom in on the tools themselves. When geneticists talk about past population size, they're not reading a number off some ancient census tablet. They're looking at three main kinds of genetic information, each with its own quirks and blind spots. First, mitochondrial DNA. You can think of mtDNA as the matrilineal surname system of your cells. You got your mitochondria from your mother, who got hers from her mother, and so on in a single, unbroken line. No shuffling between parents, no mixing, just one continuous thread running straight back in time. Because of that simplicity, it's relatively easy to reconstruct a family tree for mtDNA. Each mutation is like a small spelling change in that inherited surname. Over many generations, different lineages accumulate different changes, and by counting and comparing them, you can infer how closely related different people's maternal lines are, and roughly how long ago they shared a common maternal ancestor. Then there's the Y-chromosome, which plays a similar role for one slice of the paternal story. Only people with Y-chromosomes have them, and they usually inherit them from their father. Again, mostly no recombination, just a chain of descent. Mutations pile up, lineages branch, and you can use those patterns to reconstruct a male line family tree. But notice the limitation. mtDNA is just one line of mothers. Y-DNA is just one line of fathers. They're like two narrow threads pulled from an enormous tapestry. Most of your ancestry is not in those threads. That's where the rest of the genome comes in. The autosomes and the X-chromosome. Everything that isn't mtDNA or the Y are recombining, shuffling mixtures of all your ancestors. Each generation, your chromosomes get cut and pasted together from your parents' chromosomes, which were cut and pasted from their parents, and so on. That makes the math harder, but the information content explodes. Instead of a single lineage, you have millions of little segments, each with its own history. Some stretches of your DNA might trace back to an ancestor 10,000 years ago, others to someone 500,000 years ago. Whole genome methods try to read this mosaic and reconstruct how the population must have been changing through time to produce it. Underneath all of these tools sits a concept called coalescent theory. Imagine you pick two people alive today and follow a tiny chunk of their DNA backwards in time, generation by generation. Eventually, you'll reach a point where both copies of that chunk came from the same ancestral copy in one individual. That point is called their most recent common ancestor for that bit of DNA. Now repeat that process for more people. Take 3, 5, 100 individuals and walk their copies of that chunk backwards. As you go back, lineages keep merging, coalescing until, at some time in the past, all of them trace back to a single ancestral copy. Do this for many independent chunks of the genome, under some assumptions about mutation rates and how populations grow or shrink, and you can infer how often those lineages had to merge in the past. If a population was small, lineages bump into each other quickly and coalesce sooner. If it was large, it takes longer for everyone's ancestry to converge. That's the core trick. You look at the shape and timing of all those mergers in genetic space, and you work backwards to a history of population size in real time. Bottlenecks leave fingerprints in this process. When a population shrinks, 3 things tend to happen in the DNA. First, overall diversity drops. With fewer individuals, more lineages go extinct by chance. Many potential branches of the family tree simply never make it through the squeeze. Second, you get long haplotypes, long stretches of DNA where most people share the same version. After a bottleneck, there are fewer distinct sequences floating around, so large chunks of genome can be identical across many individuals. As the population expands again, recombination slowly chops those long blocks into smaller pieces. so their length carries information about when the reduction happened. Third, genetic drift. The random fluctuation of gene frequencies gets stronger. In a tiny population, chance events loom large. A mutation can go from rare to common just because its carriers had slightly more kids by luck, or disappear entirely in a few generations. Drift during bottlenecks can scrub away variation and leave weird, lopsided patterns that stand out when you compare species or populations. But turning those patterns into dates is messy. To say this bottleneck happened around 900,000 years ago, you have to assume how fast mutations appear, how long a generation is on average, what the population structure looked like, and what selection was doing. Change those assumptions, and your date can slide tens or hundreds of thousands of years. That's why genetic dates almost always come with wide confidence intervals. A coalescent estimate might say the effective population size dropped sharply somewhere between 950,000 and 650,000 years ago, with a best guess around 820,000. That's not a laser pointer fixed on one particular eruption. It's more like a flashlight beam illuminating a broad stretch of time. And there's one more trap that trips people up again and again. When you hear about a mitochondrial Eve or a Y-chromosome Adam, it's tempting to picture a single woman and a single man living at the same time, from whom all of us descend, survivors of some lonely post-apocalyptic world. That's not what those terms mean. Mitochondrial Eve is simply the woman whose mtDNA line didn't die out. Other women alive at her time had descendants too, but over hundreds of thousands of years, their unbroken mother-to-daughter lines eventually fizzled. Same idea for Y-chromosome Adam on the male side. A small effective population size or a recent common ancestor for one genetic marker does not automatically mean there were only that many people alive, or that everyone else died off in some dramatic event. It means that, from the perspective of that particular piece of the genome, only a limited number of lineages successfully threaded their way through time to the present. To connect that to Toba, or to any specific catastrophe, we need more than just a shallow mtDNA tree or a tight Y-chromosome cluster. We need the whole genome picture to narrow in on the same period, across many populations, and we need environmental and archaeological records to agree. And if you're curious to dig deeper into how scientists actually do that, how they wring history out of molecules, we've put together a reading list and some recommended books on ancient DNA, population genetics, and human evolution. You can find it on our site at channel URL. Some of the authors even offered a discount code for viewers, so if you want to go past documentary level and into the details, that's a good place to start. Because to really judge claims about Toba nearly ending us, we can't just wave around the number 3000 and call it a day. We have to see what happens when this genetic story meets the dirt and the ash. So next, let's go to one of the most critical testing grounds on Earth, the regions buried beneath Toba's fallout, where archaeologists have literally been digging through the layers to see if humans vanished, or kept right on going. When geologists talk about Toba, they love India. Not because India was ground zero, it wasn't, but because it sat right in the path of the ash cloud. Across the subcontinent, in river valleys and rock shelters, there's this pale volcanic blanket sandwiched in the soil like a page marker in a book. Above it and below it you get stone tools made by humans. So the obvious question is, does the story on page before Toba look different from the story on page after Toba? If Toba nearly wiped us out, you might expect a sharp break. Tools stopping abruptly, sites abandoned, new people, or at least new ways of making things, showing up only after a gap. Archaeologists call this a cultural discontinuity, a before and after that doesn't smoothly connect. But if people in South Asia took a hit and just kept going, you'd expect something else: continuity. Same basic tool types above and below the ash. Same technological accent. maybe with gradual tweaks, but no big reset. That's exactly what makes the Indian record so important. It's a real-world test of the Bottleneck story, laid out layer by layer. Let's talk about those layers in several places in India, especially in the central Narmada Valley and parts of southern India. Archaeologists have found what look like continuous sediment stacks with a Toba ash layer right in the middle. Above and below that ash, they find what's called a Middle Paleolithic lithic industry, stone tools that follow a particular style of shaping and flaking. Same raw materials, same prepared core techniques, same forms of points, blades, scrapers. In some sites, you can literally stand there and pick up a flake from below the ash and one from above, and unless you know the stratigraphy, you'd have a hard time telling which is pre-supereruption and which is post-supereruption. That kind of pattern has led some researchers to argue for cultural continuity across Toba in South Asia. Whatever the eruption did to climate and ecosystems, it didn't erase humans from the region or force a complete technological reboot. The people using those tools, or at least their direct descendants were there before, were there after, and kept doing recognisably similar things. But not everyone is convinced, and the devil is in two phrases that sound boring but matter a lot: in situ and site formation. When archaeologists say a layer is in situ, they mean it's still in the original place it formed. Tools fell on that surface, ash settled on that surface, sediments buried that surface, and nothing since then has seriously stirred the deck. In reality, nature is messy. Floods rework sediments. Roots churn soil. Animals burrow. People dig hearths, pits and shelters. Over tens of thousands of years, layers can smear, tilt, or get mixed. A neat sandwich of tools, ash tools, might not represent continuous occupation. It might be an illusion created by later disturbance. So in India, the argument often boils down to this: are those Middle Paleolithic assemblages really lying undisturbed above and below the same Toba ash fall, or have some tools been moved up or down by water and time? Is the ash itself one single clean event, or are we seeing multiple pulses, erosion, and redeposition? Answering that is hard. You're working with thin layers, subtle differences in grain size, and dates that have error bars of thousands of years. Small mistakes in reading the sedimentary story can turn apparent continuity into a mirage, or hide a real break inside what looks like a smooth record. So archaeologists don't just look at, is there ash and are there tools? They ask deeper questions. What kinds of tools, how many, and how are they changing? When a population is under stress from climate, from lost prey species, from disease, you often see signatures in the archaeology. Site density can drop. You get fewer occupied locations, fewer layers with intense activity. Seasons of use can narrow. Instead of year-round living, you get brief visits. In some cases, toolkits become simpler or more generalized, as groups lose the time and social bandwidth to maintain complex technological traditions. In other cases, the opposite happens: rapid innovation. New hunting strategies, more efficient blades, different raw materials being pulled from farther away. A stressed population might experiment more, and those experiments can leave a trail in the stone. In the Indian Toba record, people have tried to read all of this at once. Do we see a sharp decline in the number of sites right after the ash? Do toolkits shrink to bare bones? Do new industries suddenly appear that look like outsiders moving in? The answers so far are mixed. Some regions with Toba ash show what looks like steady cultural continuity and no obvious crash in occupation intensity. The same kinds of Middle Paleolithic tools appear both below and above, with no large gap and no clear invasion of a different style. That weakens the idea that Toba simply emptied South Asia of people. Elsewhere, the record is thinner or more ambiguous. Sediments are patchy, dates overlap. A missing layer could mean people left, or that erosion wiped out the evidence. A change in tools could signal population replacement or just local innovation by the same lineage adapting to new conditions. And then there are places where the ash is present, but tools are absent entirely. Does that mean nobody lived there around the time of the eruption? Possibly it could also mean those zones were always marginal, or that later river systems have simply scrubbed the slate clean. So where is the evidence strongest? It's strongest at well-studied sites where the ash can be chemically tied to Toba. The stratigraphy is clear and the lithic assemblages are big enough to analyse in detail. Those are the cases where continuity arguments carry the most weight. Thousands of artefacts, careful excavation, multiple dating methods, and a consistent picture of humans before and after. It's most contested at fragmentary sites, or where only a handful of tools occur close to the ash, or where sedimentary processes are obviously complex. In those places, small interpretive choices can flip the narrative from "people survived here" to "this was a dead zone," and different teams draw different lines. What almost everyone agrees on, though, is that the Indian record does not shout instant, total, long-lasting human extinction in the wake of Toba. Whatever the eruption did, it left at least some humans in or near the fallout zone, still making tools, still occupying familiar landscapes, still writing their story across the page the volcano tried to tear out. But India is just one chapter. To understand how Toba's ash and cold rippled through the rest of the human range, we have to look at places that might have been sheltered, especially in Africa, the continent that would ultimately send our ancestors out to meet Neanderthals, Denisovans, and the wider world. If India sat in the path of the ash, Africa sat at the centre of the story. Whatever happened to our species around the time of Toba, it had to make sense on the African map. This is where Homo sapiens had already been living for tens of thousands of years. This is where most of our genetic diversity still resides. If there really was a bottleneck to just a few thousand breeding individuals, it almost certainly played out, at least in part, on African ground. But Africa wasn't one unified, equally blasted landscape. It was a patchwork, and in a patchwork, some tiles get hit harder than others. This is where the idea of refugia comes in. A refugium is basically a safe-ish zone in a bad time. Not completely untouched, but buffered. A place where local conditions stay just good enough that plants, animals and people can hang on, while surrounding areas crash. On a climate map, refugia tend to line up with specific features: coastlines, big lakes, major river systems, and complex topography, where mountains and valleys create their own microclimates. Now imagine Africa, 74,000 years ago, with the global climate system already in a moody, ice age swing, and Toba adding another nudge. Temperatures drop a bit, rainfall patterns shift, some regions get drier, others wetter, some just more unpredictable. If you're living in the middle of a brittle grassland that needs a very particular amount of rain, that's a problem. A couple of bad years and the whole system collapses. But if you're living along a coast, or on the shores of a big lake, or in a river valley that's fed by distant rainfall, the story changes. Even when the sky is weird and the seasons are off, tides still move. Upwelling currents still bring nutrients. Deep lakes hold thermal inertia. Rivers integrate weather over huge catchments. They smooth out the spikes. For humans, those buffered zones are gold. Think about a late Pleistocene forager band camped on an African shoreline. Inland game might be migrating unpredictably. Grasses might be failing, but the intertidal zone still floods twice a day. Shellfish, small fish in rock pools, seaweed, stranded carcasses. It's not exactly a supermarket, but it's a more stable base than chasing a shrinking herd across a drying savanna. Same with big lakes like Lake Malawi or Lake Victoria, and big river systems like the Nile, the Congo, the Zambezi. Even in cooler or drier spells, those waters can protect pockets of habitat, sustain fish populations, and keep narrow ribbons of forest or wetland alive. Those ribbons become corridors and refuges. There's a reason so many archaeologists have gotten excited about coastal adaptation and aquatic resource use in Africa during this general time frame. Sites in places like South Africa's south coast, Pinnacle Point, Clayses River, Blombos, show early, intensive use of shellfish, fish and seabirds alongside terrestrial hunting and plant gathering. That kind of broad, flexible diet is a resilience mechanism. If your band can rotate between mussels, shellfish, fish, small antelope, plant bulbs, fruits, maybe even bone marrow and brain tissue stored for lean times, you're less tied to any one ecological domino. If a drought hits and large game migrates away, you don't instantly starve. If a cold snap knocks out certain plants, you still have protein in the intertidal zone. And that's just the coast. Far inland, other African sites show people exploiting riverine and lakeside resources, fish, aquatic plants, hippos, waterfowl, mixed into a broader foraging package. The more diverse the menu, the more ways there are to cushion shocks. So what does the archaeology actually say about people riding out the Toba interval in Africa? It's not as neat as before ash and after ash, because African landscapes didn't get that same nice, datable blanket. Instead, researchers lean on tool traditions, site densities, and climate records from lakes and oceans. In several regions, we see continuity across the Toba window. Middle Stone Age industries with sophisticated prepared core technologies, tiny backed pieces, pigments and sometimes shell use appear before, during and after the likely eruption time. There's no obvious continent-wide technological crash. That doesn't mean nothing happened. In some areas, site numbers seem to thin during particularly harsh climatic phases. In others, you see shifts in raw material sourcing or tool emphasis that might signal people moving or reorganizing their subsistence. But the picture is patchy, and those shifts don't line up neatly with Toba's date so much as with broader glacial-interglacial swings. African climate records help here. Cores from lakes like Malawi and from marine sediments off both coasts suggest that around the Toba period the continent wasn't uniformly plunged into darkness and disaster. Instead, you see regional contrasts. Some zones appear to have been relatively wet or stable. Others tip into drier, more variable conditions. Monsoon systems adjust, but not all in the same direction. In East Africa, for example, some lakes show water level changes, but not necessarily a sudden, unprecedented collapse right at 74,000 years ago. In southern Africa, there are hints of cooler and perhaps drier conditions in some intervals, but again as part of an ongoing pattern of swings. In that context, refugia start to look less like rare lucky spots and more like a web of overlapping safe enough regions, shifting through time. Coastal belts in the south and east, highland pockets where moisture gets wrung out of passing air masses. Deep rift lakes holding on to water when surrounding plains dry. Riverine corridors that stay green while adjacent plateaus turn brown. Humans didn't have satellite data or climate models, but they had memory and mobility. Over generations, bands would have learned which directions held a river, a lake, a shoreline, a known wet season refuge. When things turned bad locally, they could follow those mental maps. That mobility and knowledge network may be what kept African populations from collapsing completely, even if numbers dropped and ranges shrank in places. Instead of a single uniform bottleneck caused by one blast, you get a mosaic of local contractions and local refuges, stitched together by occasional movement and gene flow. Which raises a bigger question. If Africa held these pockets of persistence, did Toba really redraw the global human map? Or did it just nudge a system that was already under pressure from longer-term climate trends? To answer that, we have to zoom back out and look beyond Africa, to Asia, to the islands of Southeast Asia, to the routes that would eventually lead humans into Australia. When we leave Africa and look toward Asia, the story gets both clearer and fuzzier at the same time. Clearer because we have this huge, obvious geological event, the Toba eruption, sitting right on top of key dispersal corridors. Fuzzier because the archaeological record in those corridors is fragmentary, unevenly studied, and in many cases underwater. Think about how humans were likely moving before and around the time of Toba. There are only so many ways out of Africa and into the rest of the old world if you're on foot, and maybe using simple watercraft. You've got the northern Levantine route up through what is now Israel, Lebanon, Syria, into Eurasia, the southern Arabian corridor across the Red Sea or Bab el-Mandeb into Arabia, then skirting along coasts and river systems into southern Iran, Pakistan, India and beyond. And once you hit South and Southeast Asia, you run into another set of constraints: mountain chains, dense forests, big rivers, and a branching set of coastal and inland pathways that either funnel you east toward Southeast Asia and Sahul or block you. Climate controls how open those doors are. In wetter periods, deserts shrink, rivers connect, grasslands expand. The Arabian Peninsula, which today looks like a massive barrier of sand and heat, can flip into a landscape of lakes, rivers and savannas. In drier, colder phases, those same spaces can become nearly impassable for foragers, depending on surface water and vegetation. Now add Toba. The eruption itself dumps ash heavily over parts of South Asia. Sulfate aerosols in the stratosphere tweak global climate for a few years to maybe decades. Monsoon systems might weaken or shift. Some models suggest cooling and drying in key corridors. Others suggest more complex, region-specific changes. The question isn't just did people die, it's did roots close? If you're a group moving along the South Asian coast or following river valleys inland, and suddenly a few bad decades make a crucial stretch of habitat fail, a particular wetland dries, a key crossing point becomes barren, a chain of waterholes disappears, your route isn't just harder. It might be gone in that sense. Toba could have acted like a temporary wall in some directions, a gate in others. But what does the evidence say in India, as we saw earlier? There are stone tool assemblages underneath the Toba ash, then more tools above it that look broadly continuous. That's one important piece. At least in some areas, people didn't vanish and then reappear thousands of years later. They kept going. As you move farther east into mainland Southeast Asia and the islands, the picture becomes spotty. Some regions show apparent gaps in site dates around the Toba interval. Others don't. Here's where we have to be careful. An absence of dated sites is not the same thing as an absence of people. Sites are tiny points in vast landscapes. They get eroded, buried, flooded, destroyed by later occupation. Dense tropical forests and deeply weathered soils are brutal on stone tools and bones. And most of our knowledge comes from a handful of excavated locales, not a systematic grid covering every river valley and hillside. So when you see a gap in the record, no known sites between, say, 80,000 and 60,000 years ago in some region, there are at least three possibilities. People really left or died out there for a stretch. People stayed, but in ways, places or densities that didn't leave neat, easy to find sites. People stayed, Sites exist, but we haven't found or dated them yet. Right now, for much of Asia, all three are on the table. This uncertainty matters a lot when we start talking about Sahul, the combined Ice Age landmass of Australia, New Guinea and Tasmania. We know that by around 65,000 years ago, maybe slightly earlier, humans were in northern Australia. That's after Toba. To get there, they or their close relatives had to move through Southeast Asia, cross a series of water gaps, and navigate a shifting archipelago of islands. Did Toba help set that up by forcing people to reroute along coasts and into maritime niches? Or did it delay things by knocking back populations in South and Southeast Asia, slowing the push towards Sahel? There are three broad narratives researchers tend to argue about. First, the reset button idea. In this view, Toba hits South Asia hard enough that local populations crash or disappear. Whatever early expansions of Homo sapiens into the region might have existed are mostly wiped out. Much later, after conditions stabilize, a new wave of modern humans expands out of Africa or Western Asia, repopulating South Asia and eventually driving into Southeast Asia and Sahul. Toba here is a hard line. Before and after are almost separate stories. Second, the detour scenario. Here, Toba is disruptive but not terminal. Populations in South Asia and nearby regions shrink, move, fragment. Some inland routes, especially those already marginal due to Ice Age climate, become too risky. In response, people lean harder on coasts, deltas and river mouths, places that remain more buffered even during a volcanic winter. That shift might encourage the development of stronger maritime skills and a more coastal-oriented dispersal. In this telling, Toba nudges human movement from inland corridors to southern coastal ones, indirectly setting the stage for the later sweep along the shores of the Indian Ocean and ultimately the crossing into Sahul. Third, the minimal effect picture. Under this model, the main drivers of human migration and expansion into Asia and Sahul are long-term glacial cycles, sea level changes, and the gradual build-up of technological and social complexity. Toba is a nasty episode, but it's riding on top of a bigger, slower pattern. People had already been pushing into these regions in pulses when climate allowed it, and they would have continued doing so whether or not a supereruption happened. Right now, the data probably lean away from a dramatic single reset. We see hints of continuity in India, evidence of Denisovan and archaic populations persisting in parts of Asia, and models of human presence in Southeast Asia both before and after Toba's date. The detour and minimal effect scenarios are harder to distinguish. Sea level throws another complication into all of this. At the height of Ice Age glaciation, sea levels were more than 100 meters lower than today. Even around the time of Toba, coastlines in many regions were farther out than modern shorelines. Those exposed coastal plains, now drowned, are exactly where you'd expect mobile, coastal adapted foragers to travel and camp. Which means a lot of the crucial evidence for how people actually moved, campsites, middens, landing spots, short-lived stopovers, is quite literally under the ocean, beyond the reach of most archaeology. When we imagine routes, we picture today's map. But the real late Pleistocene map had wide coastal shelves, island chains that are now deeply submerged, and estuaries that have vanished under modern seas. Those would have been prime real estate for any group skirting the edges of South and Southeast Asia, or preparing for the jump into Sahul. So when we ask if Toba reshaped migrations, the honest answer is maybe, but we're peering at that answer through a keyhole. We can say that dispersal corridors are climate sensitive. We can say that the eruption overlapped in time and space with some of those corridors. We can say there are intriguing site patterns and gaps. But whether those patterns reflect a true eruption-driven rerouting of humanity, a more subtle nudge layered on top of glacial cycles, or mostly our own blind spots in the record that's still being argued? What Toba definitely did, though, was remind us how contingent long-distance movement is. A few decades of altered rainfall in the wrong valley, a collapsed wetland here, a blocked strait there, and entire paths of possibility can vanish. If you want to dig deeper into these competing ideas, the reset, the detour, the minimal impact takes, I've linked some great syntheses and books at our site, curioushumanity.net, and we've arranged a mid-video discount on a couple of them if you're watching this around release. But migrations are only half the picture. To understand what Toba meant for the people already out there, in Asia, in island chains, in future Australia, we also have to look at the ecosystems they depended on. What happens to plants, animals and food webs when a supereruption dusts half a continent and cools the air? That's where we're heading next. When a volcano the size of Toba goes off, it doesn't just threaten you directly with ash and lava. It pulls the rug out from under everything you eat. Start with the plants. Ash in the air blocks sunlight. Sulfate aerosols in the stratosphere scatter and reflect light back into space. Models and ice core data together suggest regional to global cooling on the order of a few degrees, maybe more in some seasons and places, for years to decades. Plants are solar-powered, cut the light, shorten the growing season, and you choke photosynthesis. In heavily ashfall zones, it's even worse. A few centimetres of ash on the ground can act like a suffocating blanket. It clogs stomata on leaves, breaks stems, weighs down branches, and forms a crust over the soil that makes it harder for seeds to germinate and roots to breathe. Some plants can handle that. Grasses and herbs that sprout quickly from underground buds, fire followers that are used to disturbance, trees with deep roots that can wait out a bad year or two. Others, especially slow-growing forest species, are in trouble. If repeated frosts and dimmer summers hit them during key growth phases, they may fail to set seeds, drop leaves early, or die outright. Then there's fire. You might imagine ash as dampening wildfires, and in the immediate aftermath, that can be true. Wet ash, cooler air, and reduced lightning can suppress burns for a season or two. But disturbed vegetation plus later drying can set up the landscape for enormous fires once things swing back. Dead trees, stressed shrubs, tons of extra fuel lying around, all waiting for a hot, dry year 5 or 10 years after the eruption. Some climate models even suggest that altered rainfall patterns after big eruptions can create these delayed fire peaks. So you don't just get one shock, you get a sequence. Shade and cold then, in some regions, burn. Now imagine you're not a plant, you're a grazer. Herbivores are living barometers of plant health. When grass is thin and browse withers, they crash quickly. Fewer calories on the ground means smaller herds, lower birth rates, and higher mortality, especially through winters or dry seasons. For humans who hunt, that changes everything. If you're used to following predictable migrations of large herbivores across open savanna, and those herds shrink or fragment, your hunting strategy has to adapt fast. You may have to shift from big game hunting to smaller, more flexible prey, rabbits, birds, tortoises, fish. Widen your foraging radius, travelling farther between kills, which means more energy spent per calorie gained. Lean harder on plant foods and insects when animal protein becomes unreliable. Change your seasonal movements to track pockets of better vegetation, river valleys, coastal wetlands, sheltered slopes that stayed a bit warmer. Archaeologists looking at other, better documented volcanic events and abrupt cold snaps often see exactly this kind of pattern. More diverse prey species in faunal remains, more intensive processing of bones for marrow and fat, more reliance on aquatic resources where available. Humans are flexible omnivores. That's one of our superpowers. But we still run on the same basic food web. When the base of that web, the plants, takes a hit, the effects cascade upward. Then there's water. Ash doesn't just fall on land. It falls on lakes, rivers and snowpacks. It washes into wetlands and seep springs. Fine particles can clog gills in fish and amphibians, smother aquatic plants, and alter the chemistry of shallow pools. Depending on the volcano's composition, leached elements from ash, things like fluoride, sulfur, and various metals, can spike in surface water. In modern eruptions, we've seen livestock poisoned by contaminated ponds and streams for months to years after heavy ashfall. For hunter-gatherers, reliable fresh water is non-negotiable. You can move your camp when vegetation fails. You can switch prey. You can dig for roots. But if an entire region's surface water becomes intermittently toxic, full of suspended ash, or just physically clogged, your options narrow. Groups living near coastlines or big rivers would have had some buffers. Flowing water can flush contaminants downstream. Estuaries and deltas often remain productive, even when inland systems falter. High elevation springs and deep aquifers might have stayed relatively clean. Finding and defending those safe water points could become a matter of life and death. So how long does this last? How fast can ecosystems snap back? One of the most interesting things we learn from other big eruptions and from major wildfires is that nature is both fragile and ridiculously resilient, depending on where you look. Grasses and weedy plants can recolonize ash-covered areas within a few seasons, especially if the ash layer is thin and rains are decent. In favourable climates, you can see green poking through grey surprisingly quickly. Herbivore populations can rebound in a few decades if enough survivors hang on in refuges. But full ecological recovery, mature forests, complex soil communities, stabilised food webs, can take centuries to millennia. And that's without major climate shifts layered on top. Several factors slow recovery: thickness and chemistry of the ash. Deep, glassy ash can form hard pans and poor soils that take a very long time to weather. Ongoing climate stress: if the post-eruption phase is cooler and drier for centuries, tree lines may retreat, forests may fail to re-establish in marginal zones. Isolation: if a region is cut off from seed sources and animal migrants by barriers or ongoing bad conditions, recolonization is slower and less diverse. For human groups, the difference between a 5-year bad patch and a 50-year bad patch is enormous. 5 bad years, and you might stretch social networks, move more, change diets. 50 bad years, and whole regions can effectively become demographic holes, places you pass through carefully, if at all, because they just don't support stable communities. This is the key point for thinking about Toba. You don't need a global, species-killing catastrophe to have lethal effects on real people. You just need enough ecological stress in the wrong place for long enough. A valley cut off from its usual rains. A plateau whose grasses never quite recover. A chain of waterholes that stay contaminated just long enough for the local herds to vanish and never really come back. At the scale of the planet, humans can survive that. At the scale of a band of 50 people and the 100 kilometers they know intimately, it can be the end. So when we ask what Toba did to our ancestors, we shouldn't picture a single uniform disaster. We should picture a patchwork, some areas relatively buffered, others hammered, some food webs bending and bouncing back, others shattering. And into that uneven landscape walked small, scattered human groups, trying to read the new rules. In the next section, we'll look at how they may have done it, the technologies, shelters, clothing, and fire strategies that could turn a damaged ecosystem from a death sentence into something merely survivable. Start with the most basic magic trick humans ever pulled off: making fire happen when you actually need it. In a world after Toba or after any serious cold snap, fire isn't just comfort. It's the difference between a livable night and a lethal one. There are two kinds of fire use. One is opportunistic. Lightning strikes a tree, a grassland burns. You rush in after the flames to grab smouldering branches and nurse the embers for as long as you can. Many animals do some version of this. The other is controlled ignition, the ability to create flame on demand from stored tools and materials. Archaeologists debate exactly when humans shifted from mostly fire-catching to mostly fire-making, and we probably never did it all at once, everywhere. But by the time of Toba, there's growing evidence in multiple regions for repeated hearths, stacked ash layers, and burned bones that suggest people could keep fire going for very long periods and maybe restart it when it failed. In a colder, drier, ash-stressed landscape, that reliability becomes a make-or-break technology. If your group can't restart a fire after a storm, or after a risky river crossing, or after a wind gust scatters your camp, your entire strategy shrinks. You stick close to known lightning-prone trees. You avoid certain routes. You sleep cold and wet and hungry more often, and you lose the ability to smoke meat, boil contaminated water, or heat-treat stone tools. If, on the other hand, your group has mastered one or more ignition tricks, friction drills, percussion sparks with the right rocks and minerals, tinder preparation, that knowledge acts like an invisible insulation layer. You can push into more marginal territories. You can overwinter in places that would otherwise be lethal. You can respond to sudden cold snaps instead of just hoping they don't happen. And this isn't just individual skill, it's cultural. Once a band learns a particularly reliable method, that method has to be taught, practiced, corrected, and guarded. It becomes part of the group's identity. We are the ones who never lose the fire. But fire alone doesn't save you if you're sleeping in the wind. Post-eruption climates, especially downwind of big ash plumes, are often modelled as colder and more seasonal, with stronger temperature swings and potentially nastier winds over open, disturbed landscapes. In that world, shelter strategy matters almost as much as what you eat. Think of a spectrum. On one end, you've got simple windbreaks, brush piled against a rock, a shallow cave entrance partially blocked, a few poles leaned together with hides thrown over them. These can be built quickly, abandoned easily, and work fine in mild conditions. On the other end, you have semi-permanent, insulated living spaces, deep rock shelters with constructed walls, turf and branch huts sunk slightly into the ground, frames of bone or wood covered in multiple layers of hide, with small entrances to trap heat and hearths placed for maximum warmth and minimum smoke. The archaeological record around other cold periods suggests that groups who invested in more enclosed, insulated structures could ride out bad years in place, storing fuel and food, maintaining social cohesion. Those who couldn't often had to keep moving, chasing tolerable nights and usable water. A windproof, insulated shelter changes the math of survival. It lets you keep infants and elders alive through storms. Dry, wet clothing and wood, making fire maintenance easier. Run more complex tasks at night, tool making, storytelling, planning, because you're not simply shivering in the dark. Clothing slots into this same system as a mobile microshelter. We don't have wardrobes from 74,000 years ago, but by later cold phases we see needles, hide scrapers, and wear patterns on teeth and bones that strongly suggest intensive hide working. Groups in cooler parts of Africa and Eurasia were almost certainly transforming animal skins into layered garments, footwear, and wraps. Even a crude hide cape or skirt makes a massive difference when the wind picks up over ash-dusted ground. Add leggings, moccasin-like shoes, and maybe fur-lined hoods or cloaks, and suddenly you can operate in temperatures that would kill a naked primate in hours. In that sense, clothing is a climate buffer. It decouples your body from short-term weather swings. Combined with fire and shelter, it means you don't have to abandon an otherwise rich territory just because the nights are brutal for part of the year. But there's a trade-off. All of this, fire management, shelter building, hide working, takes time, energy, and local knowledge. Which brings us to a key decision for any group in a disrupted landscape. Do you move or do you stay? Mobility is one of humanity's oldest survival strategies. When a valley fails, grazers gone, water bad, plants stunted, one response is to walk away. Small mobile bands can follow river systems, coastlines, or game trails to better conditions. In the aftermath of something like Toba, this might have been crucial. Moving out of ash-choked basins, finding cleaner water, discovering ecological pockets that were hit less hard. But mobility has costs. You can't stockpile as much food. You can't build heavy, insulated structures. You're more exposed to unknown pathogens, predators, and hostile neighbours. Every new valley is a set of unknown rules: what's edible, what's poisonous, what migrates, what doesn't. Staying put, if your refuge is good enough, allows deeper investment. You can map every spring, every stand of useful plants, every seasonal animal path. You can dig storage pits, fortify shelters, and maintain a tight loop of firewood collection and hunting routes. In a long, grinding cold phase, that kind of rootedness can turn a marginal habitat into a dependable home. Most likely, different groups balanced this differently. Some became long-term residents of lake shores, caves, and coastal refuges that buffered them from the worst climate swings. Others adopted a more nomadic pattern, cycling through a network of known spots, trading permanence for flexibility. Underneath both strategies, there was one more crucial technology, even if it doesn't look like a tool: social networks. When ecology becomes patchy good here, disastrous 50 kilometers away, information is gold. Knowing which valley still has clean water, which river still supports fish, which distant group has spare hides or stone or mates to exchange, can mean the difference between rebounding and disappearing. Anthropologists studying recent hunter-gatherers often find that social ties stretch far beyond the day-to-day band. People maintain relationships through marriage, visits, gift exchange, shared rituals. In a post-eruption world, those ties are survival infrastructure. They let groups share knowledge about changing migration routes or dangerous regions, exchange mates, reducing inbreeding in tiny populations, redistribute resources when one group has a temporary surplus and another is in crisis. Some researchers even argue that our tendency to form extensive, overlapping networks is itself a product of long periods of environmental instability in our past. Volcanic winters, droughts, and cold snaps didn't just select for better tools. They selected for better cooperation, and that cooperation extended to knowledge itself. Think of a simple example. Someone in your band discovers a more reliable way to keep embers hot overnight, or a new stitch that makes hide boots last twice as long, or a better design for a windproof hut. If your social world is rich and interconnected, that trick can spread hundreds of kilometers in a few generations, long before the genes of the original inventor have gone anywhere. That's cultural evolution acting faster than biological evolution, turning one group's lucky innovation into a shared human advantage. By the way, if you're interested in how scientists piece together these ancient survival stories from microscopic ash in lake mud to cut marks on animal bones, we've worked with publishers to get a discount on some of the best books on human origins and past climate shocks. You can find curated recommendations and the current codes at historydecoded.com/books. The link is in the description if you want to dive deeper after the video. Put all of this together. Fire you can trust, shelters that tame the wind, clothing that turns a lethal chill into a nuisance, movement strategies tuned to patchy resources, and social webs that move information faster than glaciers. And you start to see why our species and our cousins were so hard to kill. Big eruptions like Toba didn't just test these systems. They refined them. In the next section, we'll turn from the how of survival to the what you'd see if you dug it up. If Toba really did crash human numbers, what kind of scars would it leave in the ground? And do we actually find them? So let's say Toba really did hammer human numbers. Not just hard times, but a true demographic crash. What would that actually look like if you were an archaeologist, kneeling in the dirt with a trowel? First, you wouldn't see a neat sign that says population reduced to 3,000. Please, excuse the mess. You'd see patterns. Imagine you're mapping sites through time in a region, river terraces, caves, open-air camps. Before the supposed crash, you've got a decent scatter of sites, hearths, stone tools, layers of ash and trash building up as people come back season after season. Then, suddenly, or as suddenly as the dating allows, things thin out. Fewer sites get used. Some areas that were once busy stop showing any new occupation layers for centuries. Where people do hang on, their deposits get thinner. Fewer hearths stacked on top of each other, less rubbish, less bone, fewer tools. It looks like the difference between a city block that's constantly bustling and one that only sees a weekend market twice a year. That's one big signature of a crash: abandonment and sparsity. Not necessarily everywhere, but in big swaths of the map. You'd also expect to see the animal world respond. If human hunters suddenly drop in number, game animals in that region may briefly rebound. In cave layers and lake sediments, you might see a shift in faunal remains, fewer cut-marked bones from heavily hunted species, more signs of animals dying of natural causes. In some models, a human crash even shows up as a temporary boom in certain prey populations. Plant life would leave clues too. Pollen grains trapped in lake mud and peat bogs record the plant communities through time. If people are burning landscapes less because there are fewer people or they've withdrawn to refuges, you might see a drop in charcoal particles in those sediments. Fire-adapted plants might retreat. Forest edges might creep back into zones that had been kept open by repeated human burning. Put together, a regional population collapse looks like this mosaic: abandoned campsites, quieter kill sites, a pulse of less charcoal in sediments, some plant and animal communities relaxing back toward what they look like without us. But here's the catch: nature is messy, and so is the archaeological record. Almost everything that would signal a population crash can be mimicked or masked by preservation bias. Sea levels rise and fall. Coastlines that might once have held dense populations can drown, taking their camps with them under tens of meters of water. Elsewhere, erosion can strip away exactly the layers you want, carving through late Pleistocene deposits and leaving you with older or younger sediments, but nothing from the critical window. Sediments can bury sites so deeply they're effectively invisible until a highway cut or a quarry slices into them by accident. Sandy open-air campsites might just blow away. Caves are better at keeping secrets, but even they flood, collapse, and remodel themselves over tens of thousands of years. From an archaeologist's perspective, few sites can mean few people, or it can mean lots of sites we simply can't see anymore. That's why researchers lean on multiple independent lines of evidence. You don't just count stone tools and call it a day. You map tool types across time and space. Do characteristic technologies suddenly vanish from a region and only reappear much later? You look at faunal remains. Are there sharp changes in hunting pressure, species targeted, or carcass processing strategies that line up with the supposed crash? You read charcoal curves from lake cores. Do local fire histories change abruptly? You track pollen shifts to see whether vegetation changes look like pure climate response, or whether there might also be a change in how much people are modifying the landscape. If you can get several of these curves, tools, bones, charcoal, pollen, to kink at roughly the same time, in the same direction, across multiple sites, your case for a demographic event gets stronger. Even then, there's a problem baked into the physics of dating. Our clocks have error bars. Radiocarbon dates have uncertainties of decades to centuries, especially as you push back toward the method's practical limits. Other techniques, luminescence, argon-argon, uranium series, have their own spreads. Take a hypothetical sharp crash that happened in 50 years. Once you date its before and after layers in a bunch of different sites, those dates smear across 400 or 500 years, sometimes more. When you graph them, what was actually a cliff can look like a gentle slope. A sudden shock becomes a gradual trend, simply because our rulers are a bit blurry at that scale. And there's one more layer of ambiguity, the difference between fewer people and different people. Archaeology is very sensitive to cultural change. Tool styles shift, raw materials switch sources, settlement patterns reorganize. A new group moves into a region, or an old group decides to hunt differently, or trade partners change, and your artifact charts go wild even if the head count stays roughly the same. So a dramatic change in stone tool style right after the Toba ash could mean a population crash and later recolonization. It could also mean the same population is experimenting with new techniques in a stressed environment, or that neighbouring groups are now using the area more. Demographic decline leaves ecological and archaeological fingerprints. Cultural change leaves some of the same ones. Untangling them is the hard part. As we turn to the scientific debate around Toba, keep that in mind. When people argue about a population crash, they're really arguing about how to read a noisy collage of bones, stones and pollen grains, and how much of that collage can truly be blamed on one volcanic catastrophe. When scientists talk about the Toba catastrophe, they're not all talking about the same thing. There are really two main versions of the story on the table, and they paint very different pictures of what happened to our species 74,000 years ago. On one end is what you could call the strong Toba hypothesis. In this version, Toba isn't just a bad year, or even a bad century. It's the defining catastrophe of late human evolution. The eruption triggers a profound volcanic winter, global temperatures plunge, ecosystems stagger, and human populations everywhere crash hard. Not just in the path of the ash, not just downwind in South Asia, but across Africa, across Eurasia, anywhere our ancestors were trying to hang on. In its strongest form, this hypothesis says Toba was the primary driver of a near-extinction event. The famous 3,000 humans left narrative is usually tied to this view. According to this story, the genetic bottleneck we see in our DNA is basically a fingerprint of Toba. The eruption culls almost everyone, scattering a few thousand survivors in scattered refuges. Everything that comes after, our global spread, our unique brain wiring, our cultural explosion, is evolution's response to that one day when the sky went dark. It's a dramatic story. It's also under heavy fire. On the other end of the spectrum is the weak Toba hypothesis. In this version, Toba is still enormous. It still throws ash across continents, still cools the climate for years, maybe decades. It devastates regions directly under its influence. Parts of India, Southeast Asia, maybe some sensitive ecosystems downwind. It absolutely makes life harder for any humans unlucky enough to be in those zones. But it's not the lone supervillain of human history. It's more like a brutal extra punch in a fight that was already underway. In the weak version, The long background of climate instability we talked about earlier, the waxing and waning ice sheets, the abrupt cold snaps, the shifting rainfall belts is already stressing human populations. Numbers may already be low. Toba adds another layer of hardship. It might trigger regional crashes, forced migrations, shuffle where people can live and how they get food. It might deepen or prolong an existing bottleneck. But it isn't the cause of that bottleneck by itself. It's one factor among several. So why the disagreement? Part of it comes down to how you weight three big lines of evidence. First, climate impact and duration. Early models of Toba's atmospheric effects assumed something close to a nuclear winter. Massive sulfate aerosols, 10 or more degrees of global cooling, decades of deep freeze. If that's right, the strong hypothesis looks more plausible. Humans living on the edge might not survive such a shock. Newer climate simulations using better reconstructions of sulfur release and more realistic climate dynamics often land on a milder picture. Cooling, yes. Disruption, yes. But maybe a few degrees for a few years to a handful of decades, tapering off rather than locking the planet into a permanent deep freeze. That kind of hit hurts, but it doesn't automatically drive every population on Earth to the brink. Second, archaeology and continuity. Excavations in India, right under Toba's ashfall, have turned up stone tool traditions that continue through the ash layer. Similar tools, same technology, before and after. That suggests that at least some human groups survived in place, rather than being completely wiped out and replaced. In Africa, where our species' main population was likely based, we don't see a sharp, obvious global break at exactly the Toba horizon. There are changes, but they're not the clean cliff you'd expect from a sudden worldwide die-off. For many archaeologists, this continuity is a serious problem for the strong Toba story. Third, genetics and timing. The genetic bottleneck signal in our DNA is real. We are a surprisingly homogeneous species compared to many other mammals, and models do suggest our effective population size dipped low at some point in the last few 100,000 years. But some point is the issue. The timing bands you get when you model ancient population sizes are fuzzy. Some analyses put major bottlenecks around 50,000–60,000 years ago, others around 100,000, others smear the contraction across a broad window. Tying that directly and uniquely to an event at 74,000 years ago requires more precision than we actually have. So, depending on how you read those three datasets, climate, archaeology, genetics, you can land in very different places. If you give heavy weight to older, harsher climate models and interpret the genetic bottleneck as a sharp, Toba-timed event, you're more likely to favour the strong hypothesis, Toba as near-extinction engine. If you prioritise the Indian continuity sites, newer climate models with shorter, patchier impacts, and more cautious readings of genetic timing, you're more likely to see Toba as an important regional catastrophe layered onto an already unstable world. The weak hypothesis. And here's the key. Both camps are looking at broadly the same data. They're not arguing over whether Toba erupted or whether it was enormous. They're arguing over noise, uncertainty, and weighting. How thick was the ash in different regions? How sensitive were particular ecosystems? Were some human populations already declining for unrelated reasons? How trustworthy are the models that convert genetic variation into ancient head counts? Change the assumptions slightly and your conclusions shift. Over the last couple of decades, the overall trend in the field has been a quiet softening. The earliest Toba papers leaned hard into the catastrophe narrative. As more sites have been dug, as climate models and genetic methods have improved, the consensus has drifted away from Toba nearly wiped us out worldwide toward Toba was a huge regional disaster and a serious global stressor, but probably not the single-handed cause of a tiny 3,000-person remnant. That doesn't make the story less interesting. It makes it more complex. Instead of one villain and one narrow escape, we're looking at a long, tangled struggle for survival where volcanoes, ice ages, shifting coastlines, and sheer luck all play roles. And if you want to dig into how scientists actually argue these points, how they build models, compare cause and debate bottlenecks, I've linked a page with recommended books and papers, plus a discount on a few of the best popular science titles at our site, humanstorieslab.com/Toba. Because to understand what Toba really did to us, we need to follow the evidence into the models themselves. That's where we're heading next. If you want to see how much the field has changed, you have to look under the hood of the models scientists are using now. The story isn't just Toba was big, therefore catastrophe. It's, given what we know about aerosols, winds, oceans, genetics and ash layers, what kinds of worlds were actually possible after that eruption? Let's start with climate modelling, because that's where Toba's punch lands first. Early simulations were fairly simple. Take a giant sulfur release, spread it evenly through the stratosphere, dim the sun the same way everywhere, and watch global temperatures fall off a cliff. That's the nuclear winter-style picture that powered the strongest versions of the Toba hypothesis. Modern models are more complicated, and that complexity matters. Instead of just dumping sulfate into a generic atmosphere, researchers now feed in more realistic estimates of how much sulfur Toba likely released, how high the plume rose, and how the particles would have formed, clumped, and settled. They include aerosol chemistry, how those tiny droplets grow, darken, or break apart as they interact with sunlight and other gases. They pay attention to seasonality. What happens if the eruption goes off at the start of the monsoon versus in a dry season? How does that change where the ash and aerosols go? They also divide the world into detailed grids and watch how different regions respond. Tropical oceans don't cool the same way as continental interiors. High latitudes react differently than equatorial rainforests. Winds and jet streams can concentrate fallout over some areas and spare others. Run those newer models and you don't get a single uniform icebox Earth. You get a patchwork. Some areas, especially downwind of Toba in South and Southeast Asia, can experience intense short-term cooling, big disruptions to monsoons, and years of failed growing seasons for plants. Other areas, especially parts of equatorial Africa, and maybe pockets along sheltered coasts, see milder cooling and quicker recovery. You still get a colder, darker world overall for a while, but it's not a clean, planet-wide, no one eats for 10 years scenario. That regional nuance is a big part of why the strong, everywhere, all at once catastrophe story has lost some ground. The atmosphere doesn't care about our love of simple narratives. On the genetics side, the tools have also changed. Back when the 3,000 people left headline started making the rounds, a lot of the work was based on mitochondrial DNA, those little loops of genetic material you inherit from your mother, and a relatively small number of markers on the Y-chromosome for paternal lines. Useful but limited. It's like trying to reconstruct an entire population history from a few family surnames. Now, researchers can look at whole genomes, millions of markers scattered across our chromosomes. They model how patterns of shared variation and rare mutations change over time as populations grow, shrink, split, and mix. That gives much richer reconstructions of ancient population sizes, but it doesn't magically erase uncertainty. One issue is that very old events blur together. If population sizes were already low or fluctuating before Toba and stayed relatively low for tens of thousands of years afterward, the genetic bottleneck you infer might represent a drawn-out squeeze rather than a single sharp choke point. Another issue is that ancient DNA, which has revolutionized our understanding of more recent history, mostly can't help here. DNA doesn't preserve well for hundreds of thousands of years in most climates, and we don't have genomes from humans who actually lived at 74,000 years ago. Almost everything we're doing is back projection, taking modern and relatively recent genomes and pushing models backward in time. So yes, whole genome methods give us better, more detailed pictures. But they still leave big error bars on questions like exactly how low did our numbers go, and exactly when did the low point happen? While geneticists and climate modelers refine their pictures, geologists and archaeologists have been doing their own high-resolution upgrade. Tephra mapping the study of volcanic ash layers is no longer just, there's ash here, it's roughly this thick. Teams now trace microscopic glass shards and chemical fingerprints of Toba's ash across lakes, ocean basins and soil layers. They tie those layers to improved radiometric dates, to ice core sulfate spikes, to changes in pollen and plankton. The result is a much sharper timeline. We have a better sense of when Toba erupted relative to other climate swings. We can see which regions got blanketed with thick ash and which only caught a dusting. We can line up ash horizons with archaeological layers and ask, who was living there? What were they doing before the ash fell, and what changed afterward? In some places, like parts of India, the story seems to be continuity under stress. Same basic tool traditions, before and after, suggesting survivors stuck it out. In other places, there are gaps or shifts that might reflect abandonment, migration, or new groups moving in. The more precise our ash maps and chronologies get, the more local and varied that story becomes. And yet, for all this detail, some of the biggest questions remain stubbornly underdetermined. We don't know exact mortality. No model will ever reliably tell us X% of humans died because of Toba. We see hints of stress, of demographic change, of survival and disappearance, but not a global body count. We don't know the exact duration of the worst human impacts. Climate models can estimate how long aerosols stayed aloft and how long cooling persisted, but humans respond to more than just temperature. Ecosystem recovery, animal migrations, plant community shifts, and social adaptations all introduce delays and feedbacks. Some groups might have suffered catastrophic famines for a few years. Others might have muddled through with chronic shortages for generations. We don't know the precise geographic pattern of human decline and recovery. Tephra thickness, climate anomalies and genetic population reconstructions all push us towards certain maps, but they don't converge on a single sharp picture. Multiple histories fit the same data. This is where scientific culture becomes as important as scientific tools. Rather than trying to force certainty, most researchers now frame their work in terms of probabilistic scenarios. Given the eruption size, the aerosol physics, the ash distribution, and what we know about human ecology, what fraction of simulations produce near extinction? What fraction produce severe but regional collapses? How often do you get refugia in East Africa, or along certain coasts, or in highlands? They run ensembles hundreds or thousands of model versions with slightly different inputs. They compare those ensembles to the patchy but real constraints we have, the continuity sites, the genetic bottleneck ranges, the tephra dates. Then they ask which families of scenarios are compatible with all of that at once. That's why you're hearing less Toba definitely almost wiped us out, and more Toba probably made an already hard world even harder. We're not watching science march toward a single dramatic answer. We're watching it carve away impossibilities and narrow in on ranges. What Toba almost certainly did, what it probably did, and what it maybe could have done under just right or just wrong conditions. And that opens the door to a bigger question that goes beyond one volcano. If Toba was just one hit in a long series of blows, what else was shaping the bottlenecks and expansions written into our DNA? If you zoom out from Toba and look at the whole late Pleistocene, a pattern starts to emerge. It isn't a calm baseline world occasionally interrupted by one giant disaster. It's a world that's already rough, already unstable, where Toba might just be one more shove on a teetering system. Start with the ice. For the last couple million years, Earth has been seesawing between colder glacial periods and warmer interglacials. Those swings aren't gentle. Sea levels can drop more than 100 meters. Rain belts move, deserts expand and then shrink. Forests advance and retreat like slow-motion tides. By the time you get to the period around 100,000 to 50,000 years ago, humans aren't living through one smooth climate curve. They're riding a staircase of abrupt jumps and stalls. Greenland ice cores show temperature changes of 5 to 10 degrees Celsius over just a few decades during some events. That's within a human lifetime. Your grandparents could be born into one climate, and your grandchildren into something completely different. In that kind of world, populations don't get to grow freely until some disaster slams them back down. The disaster is built into the background. Rainfall patterns shift. Grazing lands vanish. Coastal foraging grounds turn into inland plains. Rivers change course. Every time a habitat shrinks or shifts, local human groups get squeezed, pushed, or fragmented. Genetic models that try to reconstruct ancient population sizes often pick up signs of long-term constraint during these glacial cycles. Not a big, thriving species suddenly choked to almost nothing, but a species that may have rarely, if ever, enjoyed huge numbers in the first place. Small, scattered, living at relatively low densities for tens of thousands of years at a time. Layered on top of that climate volatility, you have other stressors that don't leave ash layers. Disease, for instance. We're used to thinking of epidemics as a problem for dense, agricultural societies, but pathogens don't wait for cities. Hunter-gatherers interact with animals constantly. They butcher carcasses, dig for tubers, drink from open water, sleep in crowded shelters. Zoonotic diseases, those that jump from animals to humans, would have been a constant risk. A small band can be incredibly vulnerable to infection. If you've only got 30 adults and a new pathogen with even moderate mortality runs through the group, you can lose crucial hunters, toolmakers, child rearers in a single season. You might survive demographically, but your chances of splitting off daughter groups or exploring new territory drop. Over time, repeated local epidemics can cap how big regional populations ever get. Then there's resource fragmentation. As environments become more patchy, wet pockets here, dry barrens there, resources stop lining up neatly in big continuous zones. Animals concentrate in some refuges and vanish from others. Plants that used to grow everywhere become limited to microhabitats, a certain slope, a certain soil, a certain fog-catching ridge. Human groups adapt by tracking those patches, specializing and defending them. But specialization is a trap. If your group depends heavily on one seasonal migration or one nut grove or one shellfish bed, and that resource fails, you have fewer fallback options. You might be surrounded by theoretical food, but if you don't have the knowledge or technology to exploit it, you're in trouble. Add to that competition from other humans. By the late Pleistocene, we're not alone on the landscape. There are Neanderthals in the West, Denisovan-like populations in parts of Asia, maybe other archaic groups in Africa we only faintly see in the genetics. Even within our species, different bands and regional populations are jostling for the same river valleys, the same migration corridors, the same caves. Competition doesn't have to mean open warfare for it to hurt. If a stronger or more numerous group establishes territory on the best water sources, you're pushed onto poorer land. If they intercept the herds upstream, your hunting returns drop downstream. If they monopolize keystone quarries, your tools get worse. Over centuries, that kind of competitive squeeze can keep your numbers low without any single dramatic massacre. Now, put all of this together. Imagine a period when background climate is trending cooler and drier. Grasslands in one area are already patchier than they used to be. Animal herds are more erratic. You've got neighbouring groups pressing in from the north, and a recent disease outbreak has thinned your elders, the people who remembered where the emergency food patches used to be in bad years. Then, on top of all that, a supereruption goes off somewhere on the planet. Ash falls on some of your last good grazing grounds. A couple of bad growing seasons kill key tree species. Rivers silt up, migratory animals detour away from their old roots. The important thing here is that Toba, or any other big event, doesn't have to create a bottleneck from scratch. It can land on a population that's already constrained, already in a long-term low-number state imposed by glacial cycles, disease, competition, and fragmented resources. Multiple stressors can stack. A moderate volcanic winter in a stable, abundant world is one thing. The same cooling in an already marginal, stressed landscape is another. This brings us back to what genetic bottlenecks actually mean. When geneticists say they see signs of a bottleneck 50,000 or 100,000 years ago, they're not literally seeing an asteroid or a mushroom cloud in the DNA. They're seeing patterns that look like prolonged small effective population sizes, reduced variation, and evidence that lots of lineages coalesce back to a relatively small ancestral pool. One way to get that pattern is a single brutal catastrophe that drives a large population down to a tiny remnant which then re-expands. But there's another way. Strong population structure. Picture dozens or hundreds of small semi-isolated groups scattered across Africa and beyond. Each one has its own local ups and downs, some doing okay, some failing, some occasionally blinking out completely. They exchange migrants now and then, but not enough to make everyone genetically uniform. Over tens of thousands of years, natural selection and drift chip away at genetic diversity inside each group. When climates shift, some branches of the family tree simply go extinct, taking their unique variants with them. From the perspective of modern genomes that can look similar to a bottleneck, not because the whole species suddenly went from 1 million to 1,000 in 1 year, but because the long-term average number of breeding individuals who actually contributed genes to the future was never that large. It's a winnowed, pruned tree, not a single branch that almost snapped. So how would we tell these scenarios apart? What kind of evidence would distinguish one sharp event from a drawn-out squeeze? One clue would be timing precision. A genuine, global, single disaster should leave concordant signals in multiple records clustered tightly in time. You'd expect a sharp kink in inferred population size from genetic models that lines up, within dating uncertainties, with a big obvious event in climate proxies or geological layers. If instead genetic reconstructions show a broad plateau of low effective population size stretching over tens of thousands of years, that's harder to match with a single eruption. It fits better with long-term demographic constraint. Another clue would be geography. If a single catastrophe nearly wipes us out, you might expect a relatively simple pattern of survival, strong evidence of human continuity in one or a few refugial regions, with big, synchronized gaps or crashes elsewhere. In the archaeology, that would look like a lot of sites going dark at once, tool traditions disappearing globally, and then reappearing from a small source. If what you see instead is messy and regional, some areas with continuity across multiple climate jolts, others with staggered collapses at different times, multiple independent centers of innovation before and after supposed disaster dates, that points more towards structured, patchy populations bumbling through a turbulent world. Genetics can also look at the shape of the bottleneck. A sudden crash and rapid recovery leaves a different statistical fingerprint on the spread of rare variants than a long, flat period of moderate small size. Researchers use methods like the site frequency spectrum and coalescent modelling to test these shapes. So far, for humans around the Toba timeframe, a lot of those reconstructions are compatible with extended low numbers rather than a single razor-sharp choke. Finally, other species offer context. If Toba or any other event truly devastated global ecosystems, you'd expect parallel, synchronized bottlenecks in many unrelated animals and plants. Some studies do find stress in particular lineages, but we don't see a universal, identical crash pattern in everything from antelopes to trees. Instead, we see a patchwork of winners, losers, and survivors shaped by local conditions. All of this doesn't let Toba off the hook. It just situates it. The late Pleistocene was already a harsh filter. Glacial rhythms, disease, fragmented landscapes, and competition were all constantly testing human resilience. A supereruption dropping ash into that mix doesn't have to be the sole cause of a bottleneck to matter. It can be one of several overlapping pressures that kept our numbers low and our lives precarious. If anything, that makes the survival story more impressive, not less. Our ancestors weren't just lucky enough to dodge one bad day. They made it through a whole era where bad days were the norm. And as we'll see next, you can tell that story, the story of near extinction, refuges and recovery, without needing to claim that one volcano reduced humanity to exactly 3,000 people. By the way, if you're the kind of person who actually enjoys digging into this kind of nuance, we've partnered with a science publisher to offer a discount on some excellent books about human evolution, climate, and catastrophe. You can check out the titles and the current offer at the link on our site. Just head over to our homepage in the description after you're done with this video. Because the real story of Toba and human survival isn't just about one eruption. It's about how fragile and how weirdly persistent our species can be when the odds are stacked against us. So let's build a survival story that doesn't need miracle numbers or cinematic extinction. Just people, landscapes, and time. Start with the ash. In some regions, especially downwind of Toba, ash doesn't fall like a light dusting of snow. It can pile up in centimetres or more, clogging streams, smothering leaves, blinding grazing animals, irritating lungs. Rain turns it into slurry. Shallow ponds get choked. The first impact for a foraging band isn't a volcano god in the sky. It's the water tastes wrong, the fish are scarce, the kids are coughing, and the nearby grazing basin suddenly looks dead. That's the resource shock. Maybe your group relied on a mosaic of grassland and woodland that now has ash blanketing the young shoots and seeds. The big herbivores shift their roots or die off in patches. Tubers are harder to find. Insects decline one year, explode the next. It's not total ruin everywhere, but the reliability is gone. The landscape you understood has turned into a set of questions. What do humans do when their map of the world stops working? They move, but not randomly. Coasts, river mouths, big lakes, and dense forests become attractive in this kind of chaos. Shorelines offer shellfish, crabs, stranded fish, resources that can bounce back quickly, even with some ash in the system. Lakes buffer climate swings and can trap nutrients. Forests, especially wetter ones, protect soils and hide a diversity of small game. Fruits and insects that don't all fail at once. You can imagine a slow, ragged drift. Inland groups in the hardest-hit ash zones breaking apart, some splinter bands pushing toward river corridors, others heading for highlands where ash fall was thinner, others hugging coastlines where tidal cycles keep clearing the shore. Not all of these moves succeed. Some bands vanish. Others find good enough refuges and hunker down. Flexibility is everything here, Groups that had already experimented with broad diets, shellfish plus plants, plus small mammals plus scavenging from large carcasses, have more options than groups tightly specialized on one resource. People who know how to dig edible roots, process bitter seeds, and cook tough foods have a literal survival edge over people who never needed to learn those tricks. And that flexibility isn't just individual, it's social. In a world of unstable resources, cooperation becomes risk insurance. Maybe 2 or 3 bands meet seasonally at a lake they all depend on. In good years, they share surplus food or mates, strengthening ties. In bad years, those ties become lifelines. A starving group can temporarily merge with a more successful one instead of being left to die. Knowledge is part of that risk sharing. If an elder remembers a coastal shell bed from a famine decades earlier, or a plant that stays edible when others fail, that memory can redirect an entire band's path. If a neighbouring group passing through mentions a valley where the ash wasn't so thick, that information can ripple outward through trading networks. Over a few bad generations, the bands with more robust information pipelines are the ones still leaving descendants. This is what a near miss can look like without turning into total extinction. Not every lineage makes it. Whole regional traditions can wink out tool styles, myths, slight genetic variants, because the groups that carried them were in the wrong place with the wrong specializations when the shocks hit. Over thousands of years, you don't need a single afternoon where humanity goes from 1 million to 3,000. You just need enough repeated squeezes so that most of the branches of the family tree quietly end. From the perspective of your DNA today, that pruning looks like a narrowing. Many possible ancestral lines terminate. A smaller subset, perhaps clustered in safer refuges, coastal East Africa, lake-rich rift valleys, forested pockets less affected by ash and cooling, are the ones whose genes echo forward. Now, to be clear, this is a constructed scenario. We don't have a fossilized script of exactly which group walked which river or which elder told which story about a hidden marsh. What we do have are ingredients that are independently supported. Patchy ash falls, regional environmental disruption, archaeological hints of continuity in some places, and turnover in others. Genetic signals of long-term small and structured populations. When we string those ingredients together, we get a plausible human-scale narrative, local disasters and resource shocks, followed by movements into refugia, buffered by cooperation, flexible diets, and the careful handing down of how to survive when things get weird. It's not as flashy as humanity nearly died one Tuesday in Sumatra, but it's probably closer to how our species actually lives on the edge. Not one cliff, but a series of narrow ledges, navigated by small groups who don't know they're carrying the future with them. If you're enjoying this mix of deep time, mystery, and how do we even know that, there's a whole lot more of it waiting for you. I've put together a book on the website that dives into 12 of the strangest, most stubbornly unexplained mysteries in science and history. Things like vanished civilizations, odd genetic signals, and cosmic events that might have brushed past our ancestors without them even knowing. There's a link in the description, and for this week there's a discount running for viewers of this video. If this kind of careful evidence, first storytelling is your thing, that book is basically this channel in written form. Alright, back to why Toba matters. On the surface it's just one volcano, one argument about whether it knocked us down to a few thousand breeding individuals or merely gave us a very bad few centuries. But underneath that is something much bigger. Toba is a test case for how we build and check stories about where we come from. Think about what we've been doing in this video. We've taken genetic data, ice cores, ash layers, stone tools, climate models, and tried to weave them into a single narrative about human survival. Every step forces us to ask the same question. Does this story actually follow from the evidence? Or are we sneaking our own fears and fantasies into the gaps? The "we nearly ended" narratives are powerful. They grab attention. They resonate with something deep in us. The sense that we're fragile, that history could have gone another way. And they get some things absolutely right. They remind us that the world is not a stable backdrop. It throws curveballs. Climate can shift on timescales that matter for families, not just forests. A single geological event can alter rainfall patterns and food webs an ocean away. The bottleneck idea captures that unsettling truth. Our existence really might hinge on a surprisingly small number of lucky breaks. Those stories also highlight something we often take for granted. Resilience isn't automatic. It's built painstakingly through cooperation, knowledge, and flexibility. When you imagine humanity squeezed down to a few thousand people, you're forced to confront how much depends on a handful of individuals not giving up, not turning on each other, not losing the skills and stories that keep children alive. But there's a downside to the extinction porn version of this tale. If we tell the story as one giant blast, everyone almost dies, the end, we simplify a messy, distributed process into a single cinematic moment. We turn complex population dynamics into a cliff edge. That can distort how we think about risk today. Real collapses and real recoveries usually look more like what we just walked through. Patchy impacts, slow grinding losses, unequal suffering, some lineages quietly disappearing while others hang on. No single Tuesday where humanity almost blinks out, but a long stretch of Tuesdays where life is just a little bit harder and then a little bit harder again. The same is true for low probability, high impact events in our own time. Yes, supereruptions are still possible. So are pandemic pathogens we haven't met yet, asteroid impacts, runaway feedbacks in the climate system, technological accidents we haven't even imagined. The Toba debate is a reminder that even rare events deserve serious attention, not because we should live in fear of them, but because their consequences unfold through ordinary human choices. Who gets to move to the safer regions? Who maintains social ties across stressed landscapes? Who hoards and who shares? Whether we invest in early warning, in redundancy, and the sort of boring infrastructure that makes drama less likely. When we look back 74,000 years and ask, did humans almost die out? We're really also asking, how do complex systems break? How do they bend? And what makes the difference between a near miss and a final fall? The honest answer right now is, we don't fully know. The genetic data hint at long periods of low, structured populations, but don't point a big flashing arrow at Toba. The archaeological record near the ash suggests continuity, but with room for regional disruption. The climate proxies show some cooling and instability, but they're still being refined. So what would it take to move this from maybe to we're pretty confident? More genomes, especially ancient ones, from regions directly affected by Toba's ash. Better dated archaeological layers that bracket the eruption, so we can see exactly what people were doing before, during and after. Higher resolution climate records that let us track year-by-year changes in temperature and rainfall. Maybe one day, a perfectly preserved site where we can see a community's toolkit, diet and mobility pattern straddling the eruption itself. If those pieces all lined up, strong genetic narrowing at the right time, clear archaeological breaks in multiple regions, climate records showing unusually sharp, prolonged cooling, we'd have a much stronger case for Toba as a global population squeeze. If they refuse to line up, no matter how much data we add, we'll have to accept that the big bottlenecks in our story came from something else. Until then, we're in this strangely fertile space between certainty and ignorance. We know humans have lived close to the edge many times. We know supereruptions can in principle transform the planet. We know our ancestry passed through narrow gates. we still don't fully understand. The open question is, which future discovery will finally let us say, this is what really happened when Toba blew? And when we get that answer, will it make us feel safer about our place in the world, or more aware of how delicately it all hangs together? So, after all of that, what can we actually say without hand-waving about Toba and that dramatic humanity was reduced to 3,000 people line? We can say this with confidence. Toba was real, and it was huge. It was one of the largest eruptions in the last couple of million years. It dumped ash over an area stretching from the Indian Ocean to the South China Sea. In some places that ash blanket is meters thick, in others it's a thin dusting. But it's there, a timestamp baked into the ground. We can say that this ash didn't just sit prettily on the landscape. It killed vegetation locally. It loaded rivers with sediment. It collapsed roofs, smothered wetlands, and turned some regions into short-term disaster zones. If you were living close to the caldera, this wasn't a backdrop. It was the end of your world. We can also say that Toba changed the atmosphere. When you inject that much sulfur and fine ash high into the stratosphere, sunlight gets scattered. Temperatures drop. Not evenly, not everywhere, not forever, but enough to matter. Climate models and some ice core records suggest a period of cooling and disrupted rainfall patterns after the eruption. Crops didn't fail because there were no crops yet, but wild ecosystems would have felt that shock. Shifting monsoons, altered growing seasons, stressed animal populations. So, massive eruption, widespread ash, plausible volcanic winter. Those are the solid pieces. Now, what about us? The clearest thing the evidence says is that humans were already living close to the edge long before Toba blew. Genetic patterns in our DNA point to long periods of small, structured populations. Archaeology from Africa and Asia suggests scattered groups using clever, flexible toolkits to ride out repeated climate swings. We weren't a thriving, stable global species that suddenly got clobbered. We were already balancing on a narrow ledge. When we look right around the time of Toba, the picture is mixed. In India, where the ash layer is thick and obvious stone tool traditions keep going across that boundary. The same broad style of technology is there below the ash and above it. That doesn't scream everyone died. It suggests at least some continuity, even if numbers dipped or people shuffled around. In Africa, which was probably the main reservoir of human diversity at the time, we don't see a clean global crash pinned specifically to 74,000 years ago. We do see signatures that our effective population size, our genetic head count, was low over long stretches of the Pleistocene. But the timing is smeared out. It's like looking at a long exposure photo, not a sharp snapshot. You can tell the light was dim for a while. You can't point to the exact second someone flipped the switch. And that's where the 3,000 people story comes in. That number doesn't come from a census. Nobody found a cave with a chalkboard listing all known humans. It comes from genetic models, ways of working backwards from the diversity we see today to estimate how many breeding individuals our ancestors might have had at the narrowest points. Those models are powerful, but they're also sensitive. Change your assumptions about mutation rates, about how populations were structured, about who was mating with whom and how often, and your 3,000 might become 10,000 or a few tens of thousands spread out in many small groups. And nothing in that math requires a single volcanic trigger. Long grinding climate instability, habitat fragmentation, and other bottlenecks can produce similar signals. So when you see humanity was reduced to 3,000 people by Toba, there are really 3 steps layered together. First, an estimate that our lineage passed through a relatively small effective population size at some point or points in the past. Second, an interpretation that links that low point to a specific time window. Third, a story that pins that time window to Toba, because it's a dramatic, well-dated event. Each of those steps is debatable. The first is widely supported in broad outline. Yes, our species went through narrow times. The second is fuzzier. The exact timing is still being refined. The third, the clean Toba did it, almost wiped us out. Left just 3,000 survivors is, at this point, a hypothesis, not a settled fact. It's one possible way to connect the dots, and many researchers now think it's probably too simple. That doesn't mean Toba was harmless. It likely made life significantly harder in some regions, and may have pruned certain lineages in ways we haven't fully mapped yet. It just means that turning it into the one volcano that nearly ended us is more storytelling than consensus science. So the honest version sounds more like this. A supereruption 74,000 years ago dramatically reshaped parts of the world. It probably cooled the climate for a while and disrupted ecosystems humans depended on. Our species was already small and scattered, and this event may have been one more hit in a long series of hits. But the idea that Toba cleanly drove us down to exactly 3,000 people at one moment in time is still unproven, and many lines of evidence are pushing researchers toward more complex, less cinematic histories. If you like that more careful, less Hollywood way of telling deep history, there's more where this came from. I mentioned earlier in the video that I've put together a book on 12 of the strangest prehistoric and scientific mysteries we know about, enigmatic genetic signals, climate whiplash events, lost landscapes that shaped human migration. It goes into the same kind of detail with the same what can we really say attitude. You can check it out on the website, the link is in the description, and there's a discount running for viewers. If you've watched this far, you're exactly the kind of person I make these for. So if you found this useful, or it changed how you think about near extinction stories, please tap like, hit subscribe, and share it with someone who loves this kind of deep time detective work. Drop a comment and tell me what you think about the Toba bottleneck. Does the more complicated version feel more satisfying, or do you miss the clean we almost died narrative? And while you're there, let me know where you're listening from. One of the joys of doing this is seeing people from all over the planet, descendants of those scattered bands, comparing notes in the same comment section. We may never pin our story down to a single number like 3,000 people, or a single bad year 74,000 years ago. But we can keep sharpening the picture piece by piece until the past we see is strange, precarious, and recognizably human enough to matter for the future we're building now.